So number one is all about filling the unit circle, the angles in radians, and then their corresponding ordered pairs. Now there's two ways you could do it. You can either memorize the unit circle, and I'll show you my easy way that I memorize the unit circle, or you can use the concept of reference angles. I can go over that later. And pretty much you just have to memorize quadrant one, and then everything else is symmetrical, right? So if we want to talk about memorizing the unit circle. So as I said, there's a very easy way that I memorize it. So first things first, remember that this is the positive x-axis, that is the initial side, right? And then a positive angle is defined as going in the counterclockwise direction. A negative angle is a clockwise direction. So we're going to go around the unit circle in a counterclockwise direction. And then just remember, what does unit circle even mean? That means that the radius of the unit circle are all one unit, right? The first thing I start with is, right, so as I talked about, that's the initial side, that's your 0 degrees or zero radian mark. And then 180 degrees, right, traveling in the counterclockwise direction. I keep doing that. 180 degrees is the same thing as pi radians, right? So first I start with that. And then what I do is, we travel in the counterclockwise direction, right? Is filling out the denominators of all of the radian measures. And it kind of has this like little 6, 4, 3, 2, 3, 4, 6 type of pattern, right? So I'm going to go around and I'm going to do 6, 4, 3, 2, 3, 4, 6, right? And then we're going to start again, 6, 4, 3, 2, 3, 4, 6. Right, and as I said, these are going to be all of the denominators of the radian measures. And then a super easy way to remember it, I guess I could do red or pink, whatever. Everything in this quadrant is going to be pi. I'll talk about all of this, what this means. This quadrant is all going to be one less. This quadrant is one more. And then in this quadrant 4, you just have to memorize it's 5, 7, 11. So it's a good thing there's that store 7-Eleven. So that's easy to remember. So these are all talking about the numerators, right? So the numerators of this quadrant 1, as well as that quadrantal angle here at 90 degrees or pi over 2 radians, those are all pi. Next, you're going to do 1 less than the denominator. So here the denominator is 3. So 1 less than that is 2, right? 1 less than 4 is 3. 1 less than 6 is 5. And then in the third quadrant is 1 more, right? So 1 more than 6 is 7, 1 more than 4 is 5, 1 more than 3 is 4, and then same thing as this quadrantal angle, 1 more than 2 is 3, right? So that 270 degree or 3 pi over 2. And then the last but not least, 5, 7, 11. So this would be 5 pi, 7 pi, and 11 pi. So those are the ways that I remember the radians going around the circle. The other way, obviously, is talking about reference angles. So what is a reference angle? A reference angle, just remember it as one of the sides of the angles has to be the x-axis, right? So here is pi over 6 is 30 degrees, right? So here is a 30-degree reference angle. Right, so again, this is all talking about the x-axis here. This angle here is also a 30-degree reference angle. So notice that both of those denominators have a denominator of 6, right? If I keep going, this angle right here is also 30 degrees. That has a denominator of 6. And then you guessed it, this here also has a denominator of 6. So those all have 30-degree reference angle. And the same thing, there's 45-degree reference angles or pi over 4, and then 60-degree reference angles, so that's pi over 3, so on and so forth. So you can look at it as that way. And so all of the denominator 6 angles are all going to be the combination. So I'm talking about ordered pairs now. The combination, so square root of 3 over 2 and 1/2, those are a married couple. They always go together. Now the question is, which one goes first, the radical 3 over 2 or the 1/2? So all the denominator 6 ones all start with radical 3 over 2. Okay, 3 is my favorite number, so I just remember it's 3. However way you want to recognize it, right? So the quadrant 2 angle, right? They all start with radical 3 over 2, as I said, all the denominators 6s, except now the signs are relative to what quadrant it is. So all of the signs in the quadrant 2 should have the x value that is negative. everything in quadrant 3, both the y and the x values should be negative. And then in quadrant 4, only the y value is going to be negative, right? So there's that symmetry. So that now all of the denominator of 4s, those are going to be the matching ones. So those are the square root of 2 over 2s. Okay, so just remember the root 2 over 2s, those are the ones that the x and the y value are the same, or you could look at it as that middle one. So all of the, as I said, the denominator 4 ones, by symmetry, right? Because those all have a reference angle of 45 degrees. Those are all going to be that combination. And then just don't forget, right, that the signs in the x in quadrant 2, I'm trying to talk and write at the same time. All the x values are negative. Here, the x and the y are the positive, so on and so forth, right? And here, sorry, in quadrant 3, all of them are negative. And then in quadrant 4, only the y value is negative. Try talking and writing at the same time, right? So let me clear this up for a second because it kind of looks busy, right? So then, as I said, so that quadrant 1, so now all the denominators of 3, and I'm not gonna go around and writing it. I'm gonna speed things up in a second. Those, as I said, the 1/2 and the radical 3 over 2, those are the married couple. So those always go together, right? So if you notice, all the denominator 3 ones are going to be that combination, because those all have 60-degree reference angles. Now, if you want to know where, by the way, these ordered pairs even come from, like they seem random to you, check out, and I'll leave a link in the description of where, so I actually do a whole video on deriving all of these ordered pairs. So let's say your teacher doesn't have you memorize the unit circle. There's still a way to figure out what the radians are, but you're just going to have to know how to add and subtract fractions. I'm not going to do obviously all of them, but I will just show you how like one scenario looks like. So if let's say, so you do for sure need to know, right? This is obviously 0 degrees and this one is 180 degrees, right? So if let's say I want to find the degree measurement of this one. Remember, we talked about that has a reference angle of 30 degrees. So how could we figure out this angle here? Well, you do 180 degrees minus 30 degrees, right? And so this would be the 150 degree mark. So with the radians, it's the same idea, right? Instead of doing 180 minus 30, now we're going to, so to translate in radians, that would be pi minus 30 degrees, which in radians is pi over 6, right? So if I were to show that real quick, you would have to know how to add and subtract fractions, right? So my pi, which is 180 degrees, minus the 30 degrees, which is pi over 6, right? And so adding and subtracting fractions, if we put this over 1, you're going to need common denominators. So if you multiply both of those by 6, right? So 6 times pi is 6 pi, 6 times 1 is 6. Drop down the minus pi over 6. So now we have common denominators. What happens if we have common denominators? You just combine the numerators. So 6 pi minus 1 pi, surprise, surprise, that would be 5 pi over 6, right? And we already knew that's what it was. So me personally, I just like to memorize the unit circle. It just makes my life a lot easier. But you can do whatever floats your boat. So now that we have the unit circle all set up, now you have to know how to evaluate the trig functions. So I'll write kind of like the little cheat sheet over here. So again, by the way, if you're wondering where all this comes from, you could take a look at that introductory video that I made, link in the description, right? So when you're asked to do the sign ratio, you're always, so you have to memorize this, always going to look at the y value of the ordered pair. And then what's the reciprocal, by the way, of the sine function? That's going to be the cosecant function, or CSC. So remember that reciprocal just means flipped. So technically, if I put this over 1, right? So for the cosecant function, you're going to be doing 1 divided by that y value, right? Or honestly, plain and simple, you just look at the y value, and I just like to say you flip the y, right? That's the other way you could look at it. So now cosine, that is going to be the x value of the ordered pair. What's the reciprocal of cosine? That's the secant function. So that's going to be 1 divided by the x value, or plain and simple, you just look at the x value and you just flip it, right? And then you have the tangent, which is everybody's favorite. That's sarcasm, by the way. because you're going to have to divide fractions a lot. So, and by the way, the tangent function is literally defined as the sine function divided by the cosine function. So that makes sense that you would be taking the y value and dividing it by the x value. What is the reciprocal of the tangent function? The cotangent function. So instead of y divided by x, you're going to be doing x divided by y, right? So again, this is like that little cheat sheet here. So now for part A, we are asked to do sine of pi over 4. So there's two things that you should be looking at. The first thing is you look at, well, actually, it doesn't really matter what you do first. I like to look at the radians, right? The pi over 4 tells us where to look. So if we look on the unit circle, the pi over 4 is right here, right? Let me make this a little bigger. So that pi over 4 tells us that we are going to be looking at that ordered pair. Now, because it's asking us to do the sine of pi over 4, now the other piece, right? So this right here tells us that we are looking at this ordered pair. And then this piece, the sine part, tells us what part of the ordered pair are we looking at. That's the y value, right? So notice that part B is very similar. We're still looking at pi over 4, except, so we're looking at the same location, but now you're going to look at the x value of the ordered pair. Notice in both of these cases, both of the answers is actually going to be positive square root of 2 over 2, right? Because here in this case, the x and the y values are exactly the same. So if you were to set your calculator to radian mode and you literally punch in sine of pi over 4 and click enter, you're going to get a decimal, a repeating decimal. And then if you do square root of 2 divided by 2 on your calculator, you're going to see that they match. They're exactly the same, okay? So we're not just making up stuff here. It's actually meaning behind everything we're doing. Okay, so now we're going to look at part C, cosine of negative 11 pi over 6. So there's, instead of 2 steps, there's 3 steps. And what I mean by that is, if you notice, negative 11 pi over 6, that's not in the unit circle. So you are going to have to do an extra step. So before we take a look at that, right? So first of all, this right here, the cosine is telling us once we've figured out which ordered pair to look at exactly, we're going to look at the x value, and that gives us our answer. So let me go back. What happens if you get an angle like negative 11 pi over 6, for example, that is not on the unit circle? What do? You have to find what's called the coterminal angle. Okay, so there's a couple of things here. Terminal means the ending side. So if you remember before, I was talking about the initial side, or that starting place is going to be that positive x-axis. Now, negative and positive angles, it's just directional, okay? So a positive angle tells us we're going in a counterclockwise direction. A negative angle would be going the other way around. So if you're confused because you're like, wait, I do see 11 pi over 6, that's right here, but that's positive. And again, a positive angle, so that means we have traveled 11 pi over 6 radians, or 330 degrees, to land in that spot, right? So this right here would be the terminal or the ending side, and we would be looking at that ordered pair. However, that is not the correct answer, or that's not the correct location. So remember, 11 pi over 6 is 330 degrees. However, we're traveling 330 degrees in the other direction because it's negative. So we are traveling, as I said, 330 degrees, or 11 pi over 6 radians, going in the opposite direction because it's negative. So the correct location, you should be looking at that ordered pair. Now, some people, or should I say, it's probably split half and half that I've seen. Half the students I notice actually don't mind using kind of like the unit circle and just playing around with it, to kind of looking like it as a pizza pie, just kind of split things up and look at it visually. Other people don't like that so much, or that doesn't really click for them. What they do is they algebraically find the coterminal angle. So how are we going to do that? So let me just back up, actually. How many coterminal angles are there? There's actually infinite. So I can travel 11 pi over 6 radians, or 360 degrees, to get to that terminal side, right? We talked about that. Or maybe I could have first spun around a full revolution or 360 degrees, and then I could have traveled that extra 330 degrees. And this is all the negative, right? I can spin around as many times as I want. I can, at the same time, maybe what if I go in the positive or counterclockwise direction? That's the same thing. Wouldn't I just travel 30 degrees counterclockwise, right? So I could just go like that, right? So 30 degrees would get me to that terminal spot. So there's infinite coterminal angles, right? I could have first spun around 360 degrees or 2 pi radians and then gone that extra 30. So the reason why I took the time to talk about that is notice that I'm doing that circle, right? 360 degrees or 2 pi radians. That's how we algebraically find the coterminal angles. So how do we know whether we're going to add 360 degrees or subtract 360 degrees? You would know, right? You would just play around with it until you get an angle that is on the unit circle. Now, as you do this more and more, you might be able to get better intuition on should I add or subtract. But given we're given a radian measurement here, right? Instead of 360 degrees, that is equivalent to 2 pi radians. So the question is, should I add or subtract 2 pi radians? So I give you a little tip. When you have a negative angle, you always want to add 2 pi, right? Because if you subtract it, if I start at the negative and then just subtract, I end up even more to the negative. So we want to add 2 pi here, right? And watch what that magic happens. So adding and subtracting fractions, you need a common denominator, right? So we're going to multiply top and bottom by 6 here. Multiplication before addition. So I'm just going to copy that, negative 11 pi over 6. 2 pi times 6 is 12 pi. 1 times 6 is 6, right? To do a quick check, 12 divided by 6 does give me 2. So when we have common denominators, now it's time to combine the numerators. So negative 11 plus 12 is positive 1. So this is positive pi over 6. So negative 11 pi over 6, which means I traveled 330 degrees in that direction, is the same exact thing as traveling pi over 6 radians, or in other words, 30 degrees in the positive direction, right? And that's what we saw before. So now, once you figured out that negative 11 pi over 6 is coterminal with positive pi over 6, right? So they're equal to each other. So this is equal to cosine of positive pi over 6, right? We just saw that you land in the same spot. So again, this positive pi over 6 tells us that we are looking at this ordered pair specifically. And then this cosine is telling us we're now going to look at the x value. So the final answer is square root of 3 over 2. Okay, so now I'm going to move a little bit quicker because I went through everything that I needed to go over. And by the way, I go through everything. I have a course. You can sign up in the link below that I literally go through all of the lessons step by step, quizzes, homeworks, all that stuff. So in the meantime, I'm just going to kind of be blowing through this a little bit faster. So remember that the tangent, we are going to be doing the y value divided by the x value. And this angle here is going to tell us which ordered pair to look at. Now, if you remember on the unit circle, I know positive pi over 4 is on the unit circle. That's right here. So that's traveling in the counterclockwise direction of 45 degrees. But what is negative pi over 4? Again, it's directional. So that means we're traveling 45 degrees in the opposite direction. So negative pi over 4 is coterminal with 7 pi over 4. So these right here are coterminal angles. Okay, I'm going to abbreviate here, coterminal angles. So again, if you're not very visual and you don't like doing that, you can always do the algebraic method. And every time, how do you find coterminal angles? You either add or subtract 2 pi radians, right? So we were given negative pi over 4, and we're asked to find the coterminal angle, right? So you would add or subtract 2 pi, but I did say that if you have a negative, you always want to add 2 pi or 2 pi over 1. So to get common denominators, we'd have to multiply by 4, and 2 pi times 4 is 8 pi. 1 times 4 is 4. We have common denominators. We can combine the numerators. Surprise, surprise. Negative 1 pi plus 8 pi is 7 pi, right? So that's the algebraic method. So now, right, so this is going to give me the same answer as the tangent of 7 pi over 4, right? So now we have on the unit circle, we know that the ordered pair is going to be right here, right? So that's the terminal side. So I'll write that down. So this angle tells us we're looking at this specific ordered pair. And then, as I said before, the tangent is telling us that we are looking at the y divided by the x value, right? So this is x and this is y. So you're doing right divided by left. So that's negative square root of 2 over 2 divided by positive square root of 2 over 2. Now you can either keep change flip, or you recognize anything divided by itself is 1. A negative divided by a positive is negative. So simply put, that answer is exactly negative 1. So in part E, we have the secant of 11 pi over 6. 11 pi over 6, thank goodness, is on the unit circle, so we don't have to find the coterminal angle, right? 11 pi over 6, yeah. 11 pi over 6 is over here, so we're looking at this ordered pair. So square root of 3 over 2, negative 1/2. So this is telling us to look at negative square root of 3 over 2, negative 1/2. And then the secant, right, you have to memorize. This is telling us to do, that's the reciprocal of the cosine function. Okay, cosine is x, so this means we're going to flip the x value. So we're flipping negative radical 3 over 2, flip that, is negative 2 over radical 3. We don't care about where the negative goes. You can put that on the top or the bottom. So we did get the correct ratio, but again, in math, we hate irrational numbers in the denominator. So how do we rationalize it? You multiply top and bottom by that radical on the bottom. Always, right? Because we're not changing the value at all, because what's anything divided by itself? 1. So we're really multiplying times 1. So just disguised as square root of 3 over square root of 3. So now you multiply fractions straight across, and negative times a positive. So it's going to be negative 2 radical 3. Square root of 3 times square root of 3 is square root of 9. That's a perfect square. So the square root of 9 is just 3. Cosecant of pi over 6. Okay, good. So pi over 6 is on the unit circle. So the pi over 6 tells us we are looking at positive square root of 3 over 2, 1/2. So this is telling us positive square root of 3 over 2, 1/2. This right here is telling us to flip the y value, because it's the reciprocal of the sine function, and sine is y. So this is what we're flipping. Flipping 1 over 2 is 2 over 1, and 2 divided by 1, this is just 2. The next section is really properties of exponents. So for number 1, that answer is going to be D. X to the 4th power literally means multiplying the base, in this case x, how many times? Whatever the exponent is. So multiplication 4 times. That is different for number 2, which is 4 times x. So multiplication is split up with addition, right? Exponent is split up with multiplication. So that is going to be G, because that means you're adding it 4 times. So whatever the coefficient says. Number 3, 8x to the 5th, that is going to be A. So obviously 4 times 2 is 8, and then that's the product rule. The product rule says that you add the exponents. So 3 plus 2 is 5. That's different for number 4. That's going to be B, right? So that is the power rule. So remember that the imaginary exponent here is 1. So whenever you have something, a power raised to another power, the power rule says you're going to multiply, and you're technically like distributing that exponent. So a lot of people would forget to also raise the 2 to the 3rd power as well. And then 2 times 3 is 6. 2 to the third is 2 times 2 times 2, which is 8, right? Another way you could have done it is, as we talked about earlier, raising something to a power means multiplying the base that many times. So that's 2x squared times itself 3 times, right? And then that becomes product rule where you add up the exponents. 2 plus 2 plus 2 is 6. Number 5, that is going to be f. So that is the quotient rule. 4 divided by 2 is 2. And then the quotient rule says you subtract the exponents. Number 6, that correct answer is h. So that would be combining like terms. In order for it to be like terms, you have to have the same base. In this case, they're both x's, and the exponents have to match. And so when you have like terms, you're just adding the coefficients together, right? So those are practically, that's 1 plus 1. And you leave the exponent the same, right? When you add and subtract like terms, the exponents stay the same. When you multiply and divide, then that's when the exponents change. So for number 7, that is going to be C. Speaking of like terms, the only like terms are negative 4x and 2x because, as I said, you have to have matching exponents. So you just combine the coefficients. So negative 4 plus 2 is going to be negative 2, and then keep that as x to the first power, right? So then we end up with 2x squared minus 2x. Last but not least, number 8, the reason why that is going to be E, that's the negative exponent rule. So whenever you have a negative exponent, you could think of it as it moves, right? If it's in the numerator, it goes to the denominator. If it's in the denominator, it goes up to the numerator. And in that process of moving, the negative exponent turns positive. So just keep in mind, right? So that is 2x to the negative 2. Keep in mind that the imaginary exponent of the 2, base 2, is 1. So notice the 2 has a positive exponent. Only the negative exponent bases are the ones that move, right? So this is technically over 1. So again, this is the base that has a negative exponent. So that's the one that moves. The 2 stays at the top. And then, as I said, when whoever moves, that exponent turns positive. So now we're going to match the types of functions. So the first one, periodic. A periodic function literally means that it has to be a function, right? So it passes the vertical line test. But periodic means that it returns to the same value at regular intervals, right? So sine and cosine waves or functions, those are classic periodic functions, right? Notice you have that oscillating. They return to the same value at regular intervals. So that is why the correct answer for number 1, that is going to be h, right? So then for number 2, we got a linear function that is going to be g, right? So remember h of x, the other way I could write it, that's the same thing as y equals, right? They're all y equals. But we call this one the h function, so h function. So that's y equals 4. That is going to be a horizontal line, right? Crossing at the y value 4. Quadratic, so that is where the degree or the highest exponent is 2. So that is going to be d, right? So the highest exponent is 2, so therefore that would be a parabola. A cubic function is where the highest exponent is going to be 3. So that's going to be part E, right? So here's that highest exponent there. A rational function, that's part B. That is pretty much just a polynomial over another polynomial, right? So remember, ratio is in the word rational. Now there's 3 different ways that you can write ratios. One of the ways is you can write them as a fraction, right? So it's, again, you could think of it as a polynomial over another polynomial. Number 6 is obviously easy. A logarithmic function would obviously have to have a log in it. Or I shouldn't laugh because maybe that's not obvious to some people. But anyway, so number 7, a piecewise function. So it's 2 pieces of different lines, or maybe one could be a line, one could be a parabola, right? So it's pieces of different functions together on the same graph. So that is going to be part A, right? So it's 2 functions on the same graph. We got a linear function up top with a specific domain, and we have a quadratic, a parabola on the bottom with a specific domain, right? So a piecewise function, it has to be a piece of it. So notice you're always going to have a comma, and then you're going to be given the domain of that function, right? Or else if it's all real numbers, it's not a piece anymore, right? Then it's the full line. So now number 8, an even function, that is going to be part C. So first of all, an even function is defined as graphically something that is symmetrical over the y-axis. An odd function has symmetry about the origin. And that pretty much means if I take a piece of paper and look at a graph and I flip it upside down, that it actually looks exactly the same. That's what it means symmetrical about the origin. So that's the difference between even and an odd function. But how are we supposed to know without graphing, right, that x to the 8th, that is an even function? So then we have algebraic definitions. So the even definition is if I were to substitute a negative x into the function and I simplify afterwards, if I get back the original function, that's the definition of even. So for example, right, so in part C, let's call, so that's the same thing as f of x, right, equals x to the 8th. So now what happens if I substitute negative x, right? So f of negative x, I'm just going to do that simple substitution, right? So either that means negative x times itself 8 times, or if you happen to know the shortcut, whenever you have something raised to an even power, it's always positive. Anything raised to an odd power, it's always negative, right? So that way we do get the original function, right? So negative x times itself 8 times, or you recognize it's to the even power, that does simplify to x to the 8th, which actually that is the original function, right? So that's why it's even. Odd, the difference with that is we're going to do the same idea. You're going to substitute the negative inside the function. And then when you simplify, what happens is if I go, if that negative comes out, right? So in other words, now the negative, so that's the same thing as negative f of x. That is the definition of the odd function. And as I said, graphically, it would look like it's symmetrical across the origin. So number 9, that is going to be j, okay? So if I substitute negative into the function, remember, if you have something raised to the odd power, then it's going to give me a negative, right? So I guess I'll continue it down here, right? So, or I can multiply negative x times itself 5 times, but regardless, we simplify it that way. And then remember that x to the 5th is f of x. So I just drop down the negative, and this I can make that substitution, right? So notice, yes, we have just proved that it's an odd function. And number 10 is super nice and easy. That is going to be letter F. Exponential function is where the x is in the exponent. All right, so notice that all of those functions are labeled, right? F function, D function, so on and so forth. So now we're going to evaluate. So f of negative 3, so all this entire section, they're all substitution question. That's what it means. Substitute. No, that's not right. No, that is right. Okay. Well, now that I got my spelling down, so what are we substituting? So we are substituting a negative 3 where? Always into the x spot in which function? The f function. So we're going to go up. The f function is this one, right? So notice, as I said before, we are substituting negative 3. Now, so when we do piecewise functions, you can't just plug it into both, right? It depends on the domain. So we are plugging in, as I said, x equals negative 3. So how do we know where to plug it in? The top function or the bottom function? Well, that is why, as I said, we're looking at the domain. So this top one is we can only substitute x values that are equal to 2 or bigger. Is negative 3 greater than or equal to 2? No. The bottom one says we can only substitute x values that are smaller than negative 1. Ding, ding, ding. That is the one that we are going to substitute in. So remember, this is the function. So I'm going to just write down, so f of x is equal to negative x squared, right? So if I substitute it, so this, let's see. So let me start out with, so f of positive x is equal to negative x squared, right? So now we are substituting negative 3. Now be careful, whenever you substitute, I always like to tell people, you always hug the parentheses around the x. So you should actually be careful, have a negative on the outside of the parentheses. super careful, right? Because now we're doing PEMDAS. So first you square -3, negative times a negative is a positive, right? -3 times -3. So this is equal to +9. And then we're going to drop down the negative. So actually the final answer is -9. So now we're substituting f of 0. So again, always into the x spot. So we're looking at the same function. So now, as I said, we are substituting x equals 0. And if you notice, is 0, right? If I make that substitution here, is 0 greater than or equal to 2? No. Is 0 less than -1? No. So as a matter of fact, that just means this value, if you were to graph that piecewise function, 0 would not be on the graph. So the answer here, I'm just going to write does not exist. Or you can write DNE, does not exist. So now we're looking at the same function, right? These are all the f functions. So we're going to be substituting x equals 2. And so if you look, that only has to be in the top equation because 2 is greater than or equal to 2. So f of x, that function is 2x plus 5, right? So here's the function, f of x equals 2x plus 5. So now substituting 2, that's just a simple, easy substitution, right? PEMDAS, so 2 times 2 is 4, and then add. So that one is actually +9. So now we're switching function. This tells us we're substituting x equals 1, but in the d function, here is that d function right here. Nope, that's g. I don't know my alphabet, just kidding. This is the d of x function. So it's that rational function. So we are going to substitute 1 in that spot. So d of 1 is equal to 2 times 1 plus 5 divided by, be careful again, you want to hug the parentheses around the x. So you should have a negative on the outside. And then you just simplify top and bottom. So that's going to be 7 divided by 1 squared is 1, and then drop down that negative. And then 7 divided by -1, that is going to be -7. So for part E, same rational function, but now we're plugging in 0. So d of 0 is equal to 2 times 0 plus 5 divided by -0 squared. So the top would give us 0 plus 5, so that's 5. The bottom, 0 squared is 0. -0, that's just 0. So please do not say 0. 0 divided by 5 is 0, but 5 divided by 0, that is undefined. Okay, so we got a couple more. So the part F, we're looking at the C function, and we're substituting pi over 6. We are going to substitute pi over 6 in the x spot. So we're doing sine of pi over 6. So if you look on the unit circle, pi over 6, that ordered pair is going to be square root of 3 over 2, 1/2. And then the sign tells us we are going to look at the y value. So that final answer is going to be 1/2. And then last but not least, we are looking at the k function and substituting x equals 8. So the k function is a log equation. So k of 8, that is equal to log base 2 of 8. So let's say you're not allowed to use a calculator, right? So let's convert it to an exponential, right? Because exponential and logs go together. How do we convert it to an exponential form, right? So we're actually trying to find out this value. So let's say it's equal to x, right? We don't know what x is yet. So if we convert it to an exponential, that is saying 2 to the x power is 8, right? 2 to the x power is 8. So then you have to ask yourself, well, what does x have to be? X would have to be 3, right? Because 2 to the third is 8. So this answer is just going to be 3, right? X equals 3. In number 5, this is a degree 4 polynomial. Degree simply means what is the highest exponent of the polynomial. The leading coefficient goes hand in hand with the term with the highest exponent, and that is the leading coefficient. So if I were to rearrange this in standard form just means you start with the highest exponent and you go down in descending order, right? 4, 3, 2, 1. Then the leading coefficient is the coefficient or the number in front of the variable with the highest terms. Some textbooks or teachers rather might interpret the leading coefficient maybe as just like the very, very first coefficient in the front, which is 2. I have seen that before, some teachers teaching that, but from my understanding, you read the leading coefficient if you were to have it in standard form. So that's always the coefficient of the term with the highest exponent. Now the constant, very simply put, so in this case it is 1. The constant is the term that has no exponent. I'm sorry, not no exponent, no variable, okay? Right? Because it's constantly increasing by 1. That term does not change. And then speaking of terms, how many terms are there? So I like to tell people, first of all, always circle the plus and the minus signs, and that'll always kind of create like partitions as to how many terms there are. So there's 1, 2, 3, 4 terms, right? So a term, simply put, is just something that's like glued together by multiplication. All right, and then what is the maximum number of distinct roots? So distinct, or I could say unique roots, so different roots, right? Not with, not repeating roots. That's what distinct means. And what's the maximum? And the maximum amount of roots or x-intercepts or zeros, right? These are all interchangeable, is 4. And that is because the degree is 4. Okay, so if the degree was 10, right, x to the 10th power, then there's maximum of 10 roots. So that is how the theorem goes. Next one, determine whether it's even, odd, or neither. So I did talk about before, and I'll say it again, the algebraic definition is that when you substitute negative x in the function, the negative quote unquote disappears. That's what I like to tell people. In other words, you get back the original function. And that graphically means that it has symmetry over the y-axis. An odd function, to figure if it's odd, it's the same step. You still substitute negative x into the function. But I like to tell people, easy way to remember it, if the negative quote unquote comes out, then it's going to be an odd function. So in other words, there's that imaginary -1 times there, right? So I'll talk about that later, because a lot of people get confused as to how to do the odd. So you practically just pull out a -1, and then, do the distributive property. But again, if you have no idea what I just said, we can definitely do that later. All right. And then graphically odd would mean that it has symmetry over the origin. So as I said, very first step is going to be anyway to substitute negative x into the function. So again, I always tell people when you make a substitution, you always hug the x with the parentheses, okay? Super important that people get confused because there should be a negative outside of the parentheses as well as inside of the parentheses, right? We're making the substitution in the parentheses, as you can see. So plus 3, again, parentheses, negative x to the 3rd power. And then super careful, right? We're substituting negative x, notice inside the parentheses, so we should have a minus parentheses negative x, right? That's going to end up turning into positive x, right? Okay, so now we're going to follow PEMDAS. So PEMDAS says we're going to do the exponents first. So we're focusing on this, right? Negative x is the base of the exponent 5. So what's negative x times negative x, right? Times itself 5 times. It's going to be negative x to the 5th, right? So you're going to see that that sign stays negative. Or as I said earlier, the shortcut is going to be anything raised to the odd power is always going to be negative, right? So that simplifies to negative x to the 5th. And then drop down this negative, right? So notice what's the difference in what was written before and what's afterwards is notice now the 5 is inside the parentheses as opposed to outside the parentheses, right? So that's the difference. But I left the parentheses here. Technically speaking, if that confuses you, you could technically write this negative right here is an imaginary -1 times, right? So again, if that makes you feel better, you can certainly write that down. Anyway, okay, so then we're doing the other exponent. So I'm dropping down the +3 times. Again, anything raised to the odd power is going to be an odd sign. And then, right, so this is technically saying here, -1, let's see, I guess I'll keep it in red. This is like saying -1 times -x, right? So, which is going to end up being a positive, right? Or two minuses next to each other, you know, it's going to be make it a positive. So, I guess we can just write +x here since we know what that would be, right? Now we're doing the multiplications. So a negative times a negative, so this would turn into a positive times a negative, so that's going to be -3x to the third, and then drop down this +x. There are no more like terms because all the exponents are different. So now it's time we're going to ask ourselves, okay, so is it even? If it's even, it would have to be equal to the original function. Okay, this is the original function. That's -x to the 5th. Oh, stop. This is +x to the 5th. Already, it's not even, right? They have to be 100% the same. So it's not even. Now, to figure out if it's odd, reminder, this right here, there's an imaginary -1 times f of x, right? So you're always going to pull out a -1. Technically, you could just write negative, but so you're going to that's essentially you're taking out a common factor, right? So we're going to do the reverse distributive property. So -1 times what would have to give me a +x to the 5th? We need a negative, right? And then a -1 times what gives me a -3x to the 3rd. So if you see a pattern, when you pull out a -1, just all the signs are going to be different, okay? So now the question is, right? So again, I do not need this -1 here, so I'm just going to write, right? So the question is this equal to f of x, right? Because remember this negative, right? So for it to be odd, it would have to be equal to negative f of x. So you're going to look in here and you're going to compare. Is that the same thing as the f function? Well, that says -x to the 5th, right? Okay, -x to the 5th, +3x to the 3rd, yep. And then -x, yep. So that is equal to f of x. So again, what have we just done? We have substituted -x into the function. We then simplified it, pulled out a -1, and we have just proved that it's equal to -f of x. Therefore, it is odd. Okay, so if that was not equal to f of x, then the answer would be neither, right? So now it's time to find the difference quotient. This is extremely important for calc when you're going to have to find limits. You're going to have to know how to do this. So the difference quotient formula is there's 3 or 4 separate pieces that you have to know. So the main ones, if you look at the formula, is you have to separately find f of x plus h. What does that mean? You're going to substitute x plus h into the function, right? So in that spot, and then you're going to simplify it. So let's do that step first. So maybe just to stay organized, I like to do it piece by piece. So on the side, right, that first piece is we need to know what f of x plus h is. So again, we're going to be substituting x plus h in the x spot, right? We're making that substitution. So it should look like that. So after you make the substitution, now you have to simplify. Now, please don't say that's x squared plus h squared. That's not what that says. That is the same thing, right? Anything squared means you're multiplying the base times itself 2 times. So actually, you should be distributing. Now, does it matter whether you multiply those guys first, right? or if you want to multiply these two first, no, because of the commutative property. Very popular thing is people like to distribute the later two. So I'm just going to copy down that 2. Okay, so now we're distributing or foiling, whatever way you want to do it. So x times x is x squared. X times h, I could just write it as xh. Now, h times x is, I can write it as hx, right? But isn't it also the same thing as xh, right? Because of the commutative property. And that's exactly what you're looking to do when you do these problems, because if you notice now, they're like terms, okay? And then h times h is going to be h squared. And now we're going to distribute the 2 to everybody, right? Oh, actually, no. Well, you can, but as I said before, how about we combine these like terms just to work with smaller terms? So what's 1xh plus another xh? Now we have 2 xh's, right? And then it's time we can distribute the 2 to everybody. So we have 2x squared, 2 times 2, so that's going to be 4xh, and then plus 2h squared. None of these 3 terms are like terms, so that's it. So f of x plus h is equal to those 3, that polynomial, I should say. Should I define it as a polynomial? I should just say those 3 terms. Okay, so what I'm going to do now is, because we know what f of x plus h finally equals, now it's time in the formula, I'm going to make that substitution in that spot. Okay, so I'm going to, let's see, just copy down the difference quotient, right? So separately, we're going to, right? So f of x plus h minus f of x all over h. Okay, so f of x plus h, as I said, we are going to substitute in there because we just found out that's what was equal to. So we got 2x squared plus 4xh plus 2h squared, right? So this was the substitution that we made. Now we're going to, so then the next part of the formula is, now we want to, trying to find a different color here. Now we're trying to subtract it by f of x. Do we know what f of x is equal to? Yes, that is equal to 2x squared. So I am going to substitute that. So minus, right, 2x squared all over h. Okay, so we made those substitutions. Do I need those parentheses? Definitely never, we never care about, we don't ever need that first set of parentheses, right? Only the second set of parentheses, because you're technically multiplying by -1, right? So that sign will end up being different. So that's 2x squared. I'm just copying down those first 3 terms. And now the only thing that will change is the sign of the f of x. So it would be minus 2x squared all over h, okay? Next, you're gonna, after you finish the stage, you made your substitutions and you simplified. Now you're going to look to see, are there any like terms that we can simplify? And pretty much almost always, terms are going to be canceling out if you did this right? So notice that the positive 2x squared and the minus 2x squared, they cancel out, okay? So then we end up with 4xh plus 2h squared all over h, okay? So after terms should be canceling out, the step after that is you should always then factor using the GCF method, okay? So notice both terms are divisible by 2, and they also have at least one h. So the GCF is 2h, right? And so whenever we substitute using the GCF method, the GCF comes outside the parentheses, right? So how many terms are there? There's 2 terms. So there should be 2 things in there, right? So 2h times what gives me 4xh, 2x. And then 2h times what gives me 2h squared. I just need a positive h. So notice now what happens is you should end up getting the h's to cancel. And so our answer is going to be left with 2 times the quantity of 2x plus h. Now, you technically, I kind of have a feeling that some teachers are going to be like, well, you didn't really need to take out this 2 here. The important thing is you really should have just taken out the h. I would honestly say, looking back after doing this, you should really just take out the h and not the 2. And the reason why, I mean, this is correct. The reason why that we don't really care about the numerical part of the GCF is because technically we're going to actually just distribute that 2 back. So that final answer should just be 4x plus 2h. Okay, so this is really the more simplified version. Okay, so technically speaking, as I'll just repeat, the numerical value of the GCF, you don't have to pull that out, but definitely the h you'll have to, because those will end up canceling out. So for number 8, there's a vocab word that you absolutely need to know. What does it mean to find the 0? It's called the 0 because you're setting y equal to 0 and solving for x. But the 0, so what happens when you do have a y value 0 and you solve for x? Graphically, that is going to be the x-intercept. So when you're asked to find the zeros, there could be 1, there could be more. That's why I put the s in parentheses. You're pretty much just finding the x-intercepts. Now, notice I said that's when y equals 0. There is no y here, but I'll talk about that in a second, okay? So we're going to solve this by factoring. And whenever you solve by factoring, super important, you have to make sure that the equation is always equal to 0. That's always like your step 1, is checking if it's equal to 0. Notice that it's not equal to 0, so you have to make it equal to 0. How do you do that? You're going to just move terms, right, across the equal sign. So the 14x there's an imaginary positive sign here. So I'm going to be subtracting both sides by 14x, right? Those are not like terms. So that's x squared minus 14x is equal to negative 24. And so then we're going to add both sides to get rid of the 24. So now we have made it equal to 0. So again, those are not like terms. So it's just going to be x squared minus 14x plus 24 is equal to 0. So let me go back to the idea of when you find zeros, it's you're setting y equal to 0. So technically the y here is if this was a function, right? If this quadratic, if we had this parabola, it would have been that, okay? So if this was a function, as I said, then you would set y equal to 0, which technically you don't have to do because that part's already done for you, okay? So now we're looking to put it in factored form. So there's so many methods. How do you know that this one's going to be the AC method? The check that you should do is 2 things. 1, it has to be a trinomial. So it has to be 3 terms, check. And it has to be a quadratic polynomial. In other words, the degree or the highest exponent is 2, check. So it could maybe not be factorable, but obviously, since this is asking you to use the factoring method, we already know it's going to be factorable. But if it's a quadratic trinomial, that should ring a bell in your head to maybe it's the AC method. So when I'm talking about A, B's, and C's, I'm talking about A as being the coefficient of the x squared term, B is the coefficient of the x, and C is the constant, right? It has no x attached to it. That's what I'm referring to, A, B, and C. And why is it called the AC method? Because very conveniently, what you're going to do is multiply A times C together. You're then going to do a factor tree for that. And then how do we know which factors to choose? We're choosing the ones that add up to whatever the B value is. So I like to tell people whenever you're using the AC method, just identify what's A, what's B, and what's C, because that'll make your life a lot easier just for organization purposes. So please don't say that A is X. A is 1, right? Coefficients. Be careful. B is not 14, it's negative 14, and C is 24, okay? So now we're going to multiply A times C together. So that's 1 times 24, which is 24. And then we're going to make a factor tree of it. Now notice that it's a positive, okay? So for example, a positive times a positive is a positive. But be super careful. You want to really get an extensive list of all the factors. And what I mean by that is don't forget a negative times a negative is also equal to a positive, okay? Don't ever forget that. So you can keep doing the factor tree, but if you happen to find one, we're looking for ones that add up to b. So if you find ones that add up to negative 14, you can stop. I mean, why even bother going on, right? What else? How about 8 and why am I blinking at right now? 3, literally had to pause this video to think about it. Having a brain fart moment here. And then -8 times -3, and then let's see, 2 times 12, and then -2 times -12. Okay, so again, we're looking for the ones that add up to b. So it's going to end up being a -2 and a -12, right? Because -2 plus a -12 adds up to -14. So now that you have those chosen factors, I'm going to put a star. Let's see. I'm going to put a star right here, okay? Why am I putting a star around the fact that that leading coefficient is 1 is because when the leading coefficient is 1, there's a beautiful shortcut. You don't have to convert it to 4 terms and then factor by grouping. We'll do that later. Okay, so when a equals 1, the shortcut method is then you're just going to pop those factors inside the template, and this is the template. Now that plus sign can turn to a minus, it just depends on the problem, right? So it's always going to be 2 parentheses and then x and x. As I said, then you're just going to substitute, right? So since actually both of those are negative, we can just write -2 and then -12. We are done. Does it matter which one you put in which parentheses? No, because of the commutative property. So you could have done -12 and then -2. If you wanted to do a check and foiled or use the distributive property and simplified, you would see that you do get back the original. Oh, we're not done. So now we got it into factored form. Remember, this was an equation that was set equal to 0. So what we did is we converted something that was in standard form, right? And we converted it to factored form. Why would we want to do that? Because anytime you solve a factored form equation equal to 0, you do the same thing every time. You're going to then set each expression inside of the parentheses separately to 0. So you're going to have 2 completely separate equations. Now, if, by the way, totally changing the problem for 1 second, just bear with me. Let's say on the outside, you have, let's see, like 2x. Let's say you did the GCF first and you pulled out a 2x. You would have to set this equal to 0 as well, okay? But if you had just a number, right? So let's say the GCF was 2, you could just disregard that 2, right? Because technically speaking, you could just divide both sides by 2 and those 2's cancel. Okay, so what the heck did I just say? So to recap, if you happen to have a variable on the outside of the parentheses, you're going to set that equal to 0. Okay, so one of the solutions of that would always be 0. If you have a numerical value outside the parentheses, you could just disregard it or just divide it out, which is why you can disregard it, right? So anyway, you're going to end up with 2 completely separate equations that you're solving, okay? So you're going to set x minus 2 equal to 0 and x minus 12 equal to 0. Okay, and there is a shortcut when the leading coefficient is 1. Essentially what happens is the signs would just change, right? So you don't have to show all the steps. So here are the zeros or roots of the function. So if you were to graph this parabola, you know that this ordered pair would be on the x-intercept and this would be an x-intercept. Okay, that's what the connection is. Now let's look at a scenario where a is not 1. Okay, so remember that very first step, as I said earlier, is you have to check, is it equal to 0? No, it is not. Okay, so you should be adding 2 to both sides first, or else that's going to screw up your C value. Okay, your C value should not be -2, it should be +2. So now that it's equal to 0, you can now identify what's A, what's B, and what's C, right? So A would be 2, B is 5, and C is also 2. Next, you're going to multiply A times C together. So 2 times 2 is 4, and then you're going to be doing factor tree of that. So as I said before, you can do this part in your head, but I'm just showing visually everything, right? So in this case, you should also have same signs that should be multiplying together, because when you multiply same signs, you get a positive answer. If, let's say, you were doing a factor tree of -4, then you would just do opposite signs, right? Because a positive times a positive, or sorry, a positive times a negative and whatever. So a negative times a negative, and then 2 times 2, and then -2 times -2, right? So we're looking for factors of A times C that add up to B, that rhymes. It's nice and easy to remember. So which of these adds up to a positive 5? That's going to be 1 and 4. So these are the guys that we want. So again, this is not a problem where A equals 1. This is now A equals 2. So anytime you have any A value that's not 1, you're then going to have to do a lot more steps, okay? But let me back up. So remember, if A was 1, then this would be the answer, okay? But that doesn't work here, because if you distribute x times x is x squared, that's already wrong, because we already know that's 2x squared, right? So that's why that doesn't work. Why is my eraser? Let me do this. Yeah, okay. So next, when you pick out your factors, the next step is we are always going to split up that B term into 2 parts. Which parts? Well, the chosen factors are going to end up being the coefficients of that. So let me ask you, doesn't 1x plus 4x equal 5x? Yes. Could you have switched it and said 4x plus 1x? Yes, because of the commutative property. So it doesn't matter which one you do. You'll get the same answer one way or another. So then I'm just going to drop down, so 2x squared plus, and then bring down that plus 2. So this is the exact same polynomial. We just converted it from 3 terms to 4. Why the heck would we want to do that? Because then the very last thing that you do to factor is now you want to factor by grouping, okay? Now we like that shortcut method, don't we? All right, so now the factor by grouping is essentially the GCF method 3 separate times. So the GCF of this group, but what do both terms have in common? They have at least 1x. And this group here, they both have a 2. So again, when you factor using the GCF method, that GCF goes on the outside of the parentheses, and you're doing the reverse distributive property. How many boxes should go in there? 2, because there's 2 terms, right? So let's do that first group first. So reverse distributive property. So x times what is equal to 2x squared, 2x. And then x times what is equal to 1x, a positive 1, okay? The next group I could, maybe I'll do in red. So now I'm going to pull out a positive 2. Don't forget that plus sign there. It's super important. And again, there should be 2 boxes because there's 2 terms. So 2 times 2x is 4x squared. And then 2 times a positive 1 gives me 2, right? Remember, this is set equal to 0. So we're not done. There's actually 2 terms. So what do both of those terms have in common? They both have a parentheses 2x plus 1. So you're going to do the GCF method one more time. So when you end up with this step, then the reason why you know you did it correct is because the parentheses match. If the parentheses do not match, either you did it wrong or it's not factorable, okay? So the popular thing people do is they first like to write the matching parentheses, although with the commutative property, it doesn't matter. And then what goes in the second parentheses, I like to circle, so it's whatever is left over. So that should be x plus 2. Okay, and again, you can do a check. If you distribute or FOIL, you get back the original. So we're not done. All of that work was just a factor. So what did I say before? Whenever you have a factored form equation set equal to 0, you're then going to set separately each of those expressions inside the parentheses to 0. So you're solving 2 completely separate equations. On this side, if you subtract 1 and divide by 2, x is -0.5 or -0.5. That's one of them. And on the other side, you can subtract 2 on both sides. So these are the 2 roots. In number 9, we're going to factor each polynomial completely. And by completely, what that means is you're just going to factor until you can't go anymore, right? So you could use multiple different methods, or it's pretty much just breaking it down. So before we even start, the very first thing I always tell people is always look for GCF method first before doing anything. That should be your number one bell in your head is, does it have a GCF? And then you can go from there and do like a lot of, the fancier methods. So if you look at these two terms, yes, they do have a GCF, okay? What do they both have? So they both are divisible by 9, and they both have at least 2 x's, okay? So it's going to be x squared. And a little shortcut method, by the way, whenever you're asked to find the GCF, it's always going to just be you take the smaller exponent. Now, do we want to take a negative 9x squared or a positive 9x squared? They're actually both correct. So I'll show both ways, okay? So the first one, given I wrote positive 9x squared, I'll do that first. So again, when you are factoring using the GCF method, you're always going to put the GCF on the outside the parentheses. And then inside the parentheses, you're going to put boxes. How many boxes should I put? Well, because there are 2 terms, there's going to be 2 boxes. If there was 5 terms, there would be 5 boxes, right? And so then it's just the reverse distributive property. So you're asking yourself 9x squared times what gives me a negative 18x to the 5th? Well, a positive times a negative gives me a negative, and then 9 times 2 is 18. And then the product rule says that the exponents needed to be added together to get to 5. So this would have to be to the 3rd power. And then a positive times what gives me a minus 9x squared. So again, I'm going to need a negative here. And then anything times 1 is itself. So once you factored that, you have to ask yourself, okay, so now in here, in those parentheses, can I factor? And so whenever you have 2 terms, what should go off in your head is it can either, in this case, be the difference of perfect squares, or in general, the sum or difference of cubes. Those are if they have 2 terms. So if you look, 2 is not a perfect square. 1 is, but 2 is not. So it can't be difference of perfect squares. And then you might say, oh, x to the 3rd, that's a perfect cube. But again, 2 is also actually not a perfect cube. So it turns out that you are actually done. Okay, this is the final answer. Now, if instead we took out a negative 9x squared, then the signs would just be different. So it would have been positive 2x to the 3rd, and then plus 1. These are both 100% exactly correct. So either one would have been fine, right? Because if you distributed here, you would get back the original. Okay, so for part B, so remember I said, first things first, you want to scan for the GCF. That should be the first thing on your mind. So what do both terms have in common? They both are divisible by 25, and they both have 1x, at least 1x in them, right? So actually, let me back up for a second, because I do see a lot of people mess up. They see 2 terms, they see subtraction, they're like, ooh, 25 and 100, those are perfect squares. This is going to be difference of perfect squares, and then they mess up when they put the template in, okay? Because difference of perfect squares, the square root of the first term, right? We need that. X to the 3rd, that's not a perfect square. Why is it not a perfect square? Because it has to be to the even power. Anything to the even power is a perfect square. So that's an odd number, right? And then same thing, we're going to have to take the square root of the second term. Same reason, this is an imaginary 1, 1 is odd. So because it's an odd exponent, that's not a perfect square. So you can't use difference of perfect squares. Not yet. Okay, so that's why I always stress to people, always look for GCF. That should be the first thing on your mind. So as I said, they're both divisible by 25, and they both have at least 1x, okay? So again, the GCF method, the GCF always goes outside the parentheses. There's 2 terms, so I'm going to put 2 boxes. So that should be 25x. So 25x times what gives me 25x to the 3rd? Well, I already have a 25. I have 1x, but I just need 2 more, right? Because they have to add up to 3. Okay, and then 25x times what gives me a minus 100x. So we already have an x. We don't need to add any more. But 25 times a negative 4 gives me that minus 100x, okay? So the next thing that should go off in your head is, okay, since we're trying to factor completely, now we're going to see, is this binomial factorable? And it turns out this is the one that we want to use difference of perfect squares. How do we know it's difference of perfect squares? Well, difference literally means subtraction. It has to be two terms, which it is, and both terms have to be square root. Both terms have to be perfect squares, right? And we can do a check that has to be something times itself gives me back the original, right? So I like to tell people, pretend that's not, whoops, I did not mean to erase that. Pretend that's not there, right? We'll put that back in the end. This is what we're trying to factor, okay? So whenever you try difference of perfect squares, it ends up being the product of two binomials. So you put two parentheses next to each other, and there should be two terms in each. Now, both of the parentheses are going to have the exact two terms. The only difference is one of them is going to be plus and the other one is going to be a minus, okay? So what goes in the first slot, they're both going to be the same. So the square root of the first term goes in the first spot. So these should both be x's, right? And you can do a check. Does x times itself give me x squared? Yes, it does, okay? So that's that. And then we're going to do what goes in the second slot. It's going to be the square root of the second term. You disregard that minus sign. That minus sign just tells us that we're using a template. Some people get confused on that. Someone needed to hear it. I had to say that. So the square root of 4 is 2. So that goes in this spot, okay? And that's it. Not the final answer, by the way. If I were to do the distributive property and combine like terms, you would see that the middle terms cancel and you do get x squared minus 4. So you could always do a check. But remember, this is not the original problem. This is the original problem. So just don't forget, when you factor using the GCF, just make sure, remember when I crossed this out, make sure to put that GCF back. So the final answer should look like 25x times, and then the product of two binomials. So they should all be squished together, if you will. Okay, part C. So again, I always say very first step is to scan for GCF. That should be your number one. Do all four terms have something in common? No. So then you should ask yourself, okay, how many terms are there? That should be the second step in your head. How many terms are there, right? If it's 3 terms, your bell should be, oh, maybe it's AC method. If it's 2 terms, the bell should go off saying, oh, maybe it's difference of perfect squares or sum and difference of cubes, right? Those are for 2 terms. How many terms are there in this problem? There are 4. And whenever you have 4 terms, that should ring a bell in your head that you're going to factor by grouping, okay? So 4 terms, factor by grouping. It's called factor by grouping because you're literally making 2 groups of 2 terms. That's why there has to be 4 terms. And then you're essentially doing the GCF method 3 separate times. So you're going to find the GCF of group number 1. What do both of those terms have in common? 7 and 2, there's no common factor. Both of them have x's in it. Both of them have at least 2 x's in it. And I said earlier, the shortcut is you always just take the smaller exponent. And then they both have 1 y in it. So the GCF in group number 1 is x squared y. So let's factor using the GCF method for group number 1, right? So we're going to set ourselves up. There's 2 terms, so there's going to be 2 boxes. The GCF goes here on the outside. So x squared y times what gives me 7x cubed y? Well, I need a 7, right? We have 2 x's. I need 1 more to make a 3, to make it x to the third, right? Because the exponents have to add up to 3. And it already has a y. I don't have to put another one. And then x squared y times what gives me 2x squared y. So notice that already says x squared y. We already have it. The only missing thing is a positive 2. So now we're going to find the GCF of group number 2. What do those 2 terms have in common? They both are divisible by 6, and they both have 1 y in it. So that's the GCF, right? So notice the GCF is positive. So just don't forget, super important to put that plus sign. Some people forget it. Okay, so that's the GCF. There should be two boxes because there's two terms. So now 6y times what gives us 42xy? Well, 6 times 7 is 42. I already have a y. I'm just missing an x. And then 6y times what gives me a positive 12y. That's going to be a positive 2. So we're not done yet. We have to do one more step, but the way that you know it's factorable and the way that you know you factored it correctly is that your goal is actually to get matching parentheses. So if you got matching parentheses, you did it right. So believe it or not, there's actually two terms here. So what's the GCF that both of those terms have in common? They both have a parentheses 7x plus 2. So a popular thing people do is they first copy down the matching parentheses, and what goes in the other parentheses, I like to circle it, it's whatever's left over. So x squared y plus 6y, and that is your final answer. So this section, we're going to be doing operations with rational expressions. Notice that you have to know how to factor before doing this section, because that's how you actually do these types of problems. You have to first see if any of the polynomials are factorable, and then you know that you factored it correctly when you start having stuff that cancels out, okay? So you're going to look at all the numerators and denominators and see if they're factorable one by one. So here is a binomial. Is this factorable? So again, I keep saying the very first thing that you should always be scanning for is the GCF. There is a GCF. They both have a 5, and they both have at least two x's, right? You just take the smaller exponent. So let's factor that one first. So we're going to take out the GCF. There's going to be two boxes because there's two terms. Reverse distribute, so 5x squared times this would have to be x is 5x to the third. 5x squared times this would have to be a positive 1 would give us back 5x squared. We are done. We can't factor that anymore. This binomial is not factorable. I don't know if you've ever been taught this, but if a polynomial is never factorable, if the degree or the highest exponent is 1. Notice if we're looking at this binomial here, this is to the first power, so you know for a fact you cannot factor that at all, okay? Because we always want to look to factor completely when we do these problems. Okay, so now that's the numerator of, now we're going to factor this one. Okay, so first thing is there a GCF? Nope. No, none of the three terms have something in common. Then the next thing you should ask yourself, okay, how many terms are there? There's 3 terms. When there's 3 terms, a bell should go off in your head. AC method. So let's see, I'll just do the work on the side here, right? So x squared minus 4x minus 5. So the AC method says, well, let me identify. So first you want to actually identify A, B, and C. And these are the coefficients in standard form. So A is the coefficient of the x squared term, that's 1. B, be careful, is -4, and C is -5. So, so as we did a previous problem, the AC method is factors of A times C. So 1 times -5 is -5. So now we're going to do a factor tree of that, and we want to see which one of those adds up to B. So factors of A times C add up to B. That rhymes, super easy to remember. So just be super careful. It is a negative number, so you want to write a very thorough list. So either 1 times either 1 times -5 is -5, or a -1 times a +5, right? That also works. Those have to be opposite signs. So now which one of those adds up to B? Well, if I add 1 and -5, ding, 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 that's -4. If I added these bottom two, -1 plus 5, that would have been +4. So I do want these two factors. Now I'm going to put a star around A equals 1 because whenever A is 1, there's a nice shortcut. You don't have to convert it to 4 terms and then factor by grouping. I mean, you can knock yourself out. I like the shortcut. So again, what is the shortcut? The shortcut is it should be two parentheses next to each other, and then x and x. And those two factors are just going to go in the parentheses. So since we have a positive 1, I'm going to write +1. And since we have a -5, I'm going to write -5. Does it matter which of the factors goes in which parentheses? No, because of the commutative property. Okay, so now we took care of the first fraction. The second fraction, okay, so I'm going to write times. So now you have to ask yourself, is this factorable? A little hint, whenever you have just one term, there's nothing you could do. Okay, so both of those are monomials or one term, so nothing you could do there. So I'm just going to copy that down. Okay. So now that so it kind of looks a little busy. Let me take that out. So now that we have factored everything, knock yourself out, right? How do you multiply fractions straight across, right? You can do that and then stuff cancels out that way. When you do these types of problems, you always look to simplify the diagonals. That's the fastest way. So in other words, you can see here that the 5x squared cancels out with that 5x squared, right? You look diagonally. And then stuff can also cancel vertically, right? So if you notice, this parentheses x plus 1 will cancel with this parentheses x plus 1. So the final answer is just what's going to be left over. The top, you just have 3x, and the bottom, you just have an x minus 5 left. So now we're going to be subtracting fractions. So adding and subtracting fractions, you must have a common denominator. Multiplying and dividing, you do not need a common denominator. So you're subtracting, we need a common denominator. How do you do that? You have to find the least common denominator, in other words, the LCD, right? So the fastest way, just simply put, to find the LCD is you want to multiply the denominators, right? Let me just back up for a second if you're confused. So just bear with me. Let me just completely switch gears. Let's say if I was subtracting, I don't know, 2/7 minus 3/4, right? And you have to ask yourself, okay, we need a common denominator. What would the common denominator be? Well, it would be whatever 7 times 4 is, right? So you know that the common denominator is going to be 28. And that's the same thing that we're going to do in this scenario, right? So you're going to be super careful. This is a binomial. So I would put parentheses around that, right? So I would actually just do the same thing here, right? That's also a binomial. Those parentheses are going to save us a lot, or going to make things a lot clearer for us. So I always say, again, put parentheses around those binomials. Next, so we can clearly see you're going to multiply the denominator of the first fraction times the denominator of the second fraction, right? We're multiplying this times this. So again, making sure you put the parentheses is extremely important because you should end up distributing the two, okay? So the LCD, notice I'm leaving this example here just as a reference. So the least common denominator is going to be 2 parentheses 5x plus 5, right? You're multiplying them. So let me actually jump back now. I'm going to go back and forth between pre-algebra, which is what I circled. That's going to help us segue into how we do harder problems, right? So remember in this scenario, we multiplied 7 times 4 to get common denominator 28, right? So these two we know would have to be 28, right? So this is the time now. What would you do next? You would have to multiply this times 4, right? And you would have to multiply this one by 7. Okay, so I'm kind of going as slow as I can, but at the same time, I don't want it to be a 5-hour-long video. So I did make a whole course on this with quizzes and tests and lessons and warm-ups and all that stuff. The link is down below. Anyway, right? So then you would end up having 2 times 4, which is 8, and then 3 times 7, that would be 21. And then now you have common denominators, and you would go ahead and combine the numerators, right? So we're going to do the same thing back to algebra 2, right? So the harder stuff. So the same idea, right? So you're going to multiply by the other denominator. this I'm going to multiply times 2, and this one I'm going to have to multiply 5x plus 5, 5x plus 5, okay? Now we're going to do PEMDAS, right? So we have to first multiply, and then we subtract last. So in the first fraction, we have 2 times 6, which is 12. The bottom, we have 2 times the quantity of 5x plus 5. If you want to distribute that, you can, but in these problems, a lot of the, you don't really have to, honestly, but knock yourself out if you want to. I would recommend to just leave it. Okay, then the other one, we're doing binomial 3x plus 1. That's why it was important to put those in parentheses, as we did earlier, times the binomial 5x plus 5. Simply put, you're just going to be putting those together, right? So that says 3x times 1 times 5x plus 5. And then the denominator, that says 2 times that binomial, right? So 2 times 5x plus 5, right? Look at that. We have common denominators, right? So we know we did it right. All right, so we're not going to touch the first fraction. I'm just copying it down. Minus, so now we're going to simplify this fraction. And again, we're going to use the distributive property. So 3x times 5x is 15x squared. 3x times 5 is plus 15x. And then we're going to distribute the 1. If you want to FOIL, you can. I always just distribute. So we distributed the 3x. Now we're going to distribute the 1, right? 1 times 5x, so that would be plus 5x. And then 1 times 5, so that's plus 5. And then that's all over that denominator that we didn't touch as well. And then we want to see if you can actually combine like terms. So we're still looking here. Yeah, we can combine those like terms, right? So again, I'm just going to copy down the first fraction. And if you want, you can go ahead and distribute. I have a feeling some people just might want to distribute that. Okay, so we'll do that. That's 2 times 5x is 10x, and then 2 times 5, so that would be plus 10, right? Minus, again, we didn't subtract yet, so we're just simplifying. That's 15x squared, 15x plus 5x, so that would be plus 20x, and then plus 5, right? So now that we have common denominators, you combine the numerators, so that's going to look like 12 minus this entire numerator, so it should be in parentheses, right? And then all over 10x plus 10. So now the last thing that we should do is now simplify, right? So there's like an imaginary minus 1 times. So there's like should be an imaginary distribution of that negative 1. You can look at it that way, and that is exactly why all the signs should be negative. So I hope that makes more sense now. So it should end up being 12 12 minus 15x squared. The 20x turns into a minus, and then the 5 also turns into a minus. All those signs should change, and then it's all over 10x plus 10. Last but not least, super long problem. We're now going to see if you can combine any like terms. You sure can. This 12 minus 5, right? So that's going to be, I'm just going to write it in standard form, negative 15x squared minus 20x all over 10x plus 10. Whew. So we're actually done. I'm not going to show you, but if you try to factor this, because you always want to see if stuff cancels, that's the AC method. When you do A times C, there's no factors that add up to B, right? There's no factors that would add up to negative 20. That tells you that's not factorable. So just a reminder, when you multiply and divide fractions, you do not need a common denominator. So whenever you divide fractions, we're going to turn it into a multiplication problem. You're always going to keep change flip. Okay, so we're keeping the left fraction, so I'm just copying that down. We're changing it to multiplication, and then we're going to flip that second fraction. So it'll turn into that multiplication problem that we did earlier, where we're factoring everybody, if factorable, and then stuff should be canceling out. But before we even do that, I've seen people in the past I would just strongly suggest whenever you see binomials, just put parentheses around them. So, right, because that's an entire binomial. Okay, because people will start thinking that that x and that 1 are totally separate, right? That they'll start canceling out just the x's or just the ones, and you can't do that. So you have to think of those as that, right? That's an entire binomial. And same thing if you want, right? That's a binomial as well. So I just wanted to point that out there. All right, so we're gonna try and see if we can factor everything. Now I do just want to save some time. What's the very first step that I've been saying this whole time for factoring that you should always look for? That's the GCF method. Okay, so just to save time, if you were to look at all of these 4 polynomials, none of those are factorable by the GCF. Okay, so that's always step 1. So now that none of those are factorable by GCF, now we can start looking for the fancier methods. Okay, so I'll do this one first. Okay, so again, whenever you have 3 terms and the degree or the highest exponent is 2, that should always ring a bell in your head that that's going to most likely be the AC method. Okay, so A equals 1, B is -2, and C is -3. So I already went over the AC method in depth earlier, so I'm kind of going to move a little bit quicker here. And again, I have a whole course on this if you're interested, link below. Anyway, all right, so AC method, because A times C, so that's 1 times -3 is -3. You're going to always do the factor tree, just keeping in mind you account for all of the signs, right? And then you're trying to figure out which one of those adds up to B. In this case, we're looking for -2. So if I add those together, that's going to be -2, ding, 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 right? And if I added those 2 together, I would have gotten a +2. So these are the guys I want. Now, what's nice about the fact that A is 1 is whenever you have A is 1 problem, you can do a shortcut. And that shortcut is you're going to end up multiplying 2 binomials together, so 2 parentheses next to each other. And then it'll always have both of those first terms as x. Okay, that's the template. And then what you're going to do is just pop those factors right in. So 1 is positive, so I'm going to write +1, and 3 is negative, so I'm going to write -3. Done. Okay, so if A was not 1, then we'd have to use those factors and rewrite the middle term and factor by grouping. Knock yourself out. You can totally do that, but I don't know why you would. Okay, so now I'm going to erase everything and just substitute this in that spot. All right, and I do also want to add, could I have written x -3 and x +1? Yes, because of the commutative property. All right, so now let's see if that's factorable. Okay, so whenever you have 2 terms and then it's a difference or subtraction, that should be a sign in your head that maybe it could be difference of perfect squares, and it will be difference of perfect squares. So that template is 1 is plus and 1 is minus. Now, what goes in the first slot? It's always going to be the square root of the first term, right? So both of those terms are perfect squares. That's why we can do this. So the square root of x squared is x, right? And then what goes in that second spot? That's going to be the square root of the second term, right? Which is 2. Okay, done. So x +2 and x -2. So I'm going to erase that and now put that in that spot. Next, again, over here, we have 3 terms and it's quadratic. So you definitely are going to try the AC method here. Oh, good. We have another A equals 1 problem. So we can use that shortcut again, nice and easy. So 1 times 10 is 10. And then you're going to go ahead and list the factors, but also keep in mind you have to do the signs as well, right? Positive times positive and negative times negative. You can actually stop, right? Because when you add these up, you get 7. When you add these up, you get -7. And again, we're trying to figure out the factors that add up to be +7. So our chosen factors are going to be +2 and +5, right? So again, the template, when you have A equals 1, is it's always going to be 2 parentheses x and x. And now we can substitute the +2 and +5. We are done. You could have also written that 5 term first. All right, last but not least is this factorable. So I will tell you right now, whenever you have 2 terms and the degree is 1, which it is here, the highest exponent is 1, the only way it's factorable is by the GCF, okay? When it's linear, the degree is 1. The only way it's factorable is if there's a GCF. There is not. So it is not factorable, okay? And again, putting the parentheses around x plus 1 like we did before can help us clearly see that diagonally, when we see what cancels out, this has a parentheses x plus 1 and this has a parentheses x plus 1, okay? And then diagonally, the x plus 2's also cancel. And then you have to see if things factor vertically, right? So do these cancel? No, they're not the same. So now that we have fully simplified, now we can multiply fractions. How do we do that? Straight across. So our final answer is going to be x minus 3 times x plus 5 all over x minus 2. You don't have to put parentheses now over x minus 2. You can if you want. And you don't have to FOIL the top unless your teacher tells you to. So we're done with operations, right? We don't have adding, subtracting, multiplying, dividing. You just have one single fraction. And I'm now asking you to divide those. So after I divide this trinomial by this binomial, what's the actual answer? What's the quotient, the exact quotient that we get? So the two ways that you can do it is long division or synthetic division. Now, we cannot use synthetic division. Synthetic division, you can only use if the degree or the highest exponent is 1. Okay, it has to be linear. Unfortunately, it's not linear. Notice it's quadratic. It's to the second power. So again, the synthetic is a nice shortcut, but there is a catch. So it looks like in this case, we are forced to do long division, okay? So again, I have this in my course where I have like the full lesson and I go a little slower, but for now, I'm just kind of going over it. I will, let's see, write the steps on the right-hand side. So first things first, the long division symbol goes like that. So you always put the dividend, what you are dividing, inside the long division symbol, and the divisor, what you are dividing by, always goes on the outside, okay? So now that we have that long division set up, the steps would be, so this is in like my personal words. We have, I'm just gonna write match, okay? And what are we trying to match? We're trying to match the variable terms only, okay? And then very specific matching. We're matching the ones with the highest exponent, okay? So I'll write that in parentheses. So what do I mean by that? So this has the highest exponent and this is the term with the highest exponent. So those are the ones that we're trying to match. And by matching, I'm asking, what can we multiply by, right? X squared times what can get us to 2x to the third? 2x, right? Now, after we have matched, what I'm then going to do is you're going to multiply. What are you multiplying by? You're multiplying by the entire divisor, okay? And I want to stress the entire divisor. So you should be distributing here, right? Because remember, the entire divisor, the entire divisor is a binomial. I just wanted to fix that because it was bothering me. Okay, so we should be distributing that 2x, whatever we have matched, okay? So 2x times 2x squared, which is 2x to the third. Notice they match. That was the whole point. And then 2x times 1 is going to be plus 2x, okay? So after you've multiplied by the divisor or distributed, now it's time that you are going to subtract. Now, I do just want to say, be super careful. You are subtracting the entire binomial, okay? So I like to, you don't have to, but I like to just put parentheses around it just to remind myself that I'm subtracting both of them. Because people will do a good job and they'll subtract those. By the way, the whole point of matching is to cancel out. And then they'll forget, they'll do negative 6x plus 2x and they'll get negative 4x. You're always doing top minus bottom. So that is actually saying negative 6x minus 2x. So you should end up getting a negative 8x. Okay, so that's a super common mistake. Okay, now you're gonna drop down the plus 3. So this is where we're at. So now we have to figure out, can I repeat this process again? Okay, so again, let's go back to the first step. The first step is we want to match. So can I multiply x squared times anything to get to negative 8x? And the answer is no, okay? Because the degree is 1 smaller than the divisor, right? This degree is 1, that degree is 2. There's no way that can happen. So when you end up getting something that's 1 less, you're definitely done. So we can't repeat this process again. So when you are done and you can't go anymore, this is now what's called the remainder. So we can say that x squared plus 1 goes into that trinomial 2x times plus that remainder, right? This is kind of weird when you're talking about variables. But we're not in elementary school. You can't just write r and then that remainder, right? So how do we write that? So in general, the final answer, and by the way, let me just back up. This 2x, what is that called? Let's see what color. This is called the quotient. So the result after you divide. Okay, so how do you write the final answer? As I was saying, you always write it as the quotient. So in this case, 2x plus whatever you get as the remainder over or divided by the divisor. Okay, so that's the general rule of thumb. So doing it specific to this problem, so that's going to be 2x plus the negative 8x plus 3 goes in the numerator, and then the divisor was x squared plus 1. So this is the final answer. So now we're getting into proofs or verifications. Whenever you do proofs, okay, how do you even set them up? You're going to choose or pick one side of the equation, and it's usually the more annoying looking side. So we can see that this is obviously more stuff going on. And then what we're going to do, right, is we're gonna copy it down. And then we're going to simplify, right, or make any substitution. And how do we know we are done? We are done when we have reached our goal. So you do not, please don't you dare. I see people start like, subtracting sine of x on both sides. No. Okay, do not touch that right side. That's our goal. That's how we know when we are done. Okay, so again, we usually like to start with the more annoying side. Could you start with the other side? Sure, it's just a little hard logically to figure out where we're going. Okay, so that's why we usually do that. So we're going to write equals. And now again, we're going to figure out, can we do anything with it? Can we use algebra 1 skills like factoring or order of operations, just simplifying in general? Or are there any substitutions that we can use? And it could be a mix of both, okay? So if we look at both of them, you always, a neat little trick is figuring out, seeing if there's maybe, if we can factor it using the GCF method. So how many terms are there right now? There's actually only 2 terms, right? That's a term and that's a term. Do both of these terms have something in common? Yes, they both have a sine of x. So actually this is factorable using the GCF method. Okay, so factored using the GCF method, that GCF goes on the outside. There are 2 terms, so there's going to be 2 boxes, and we're going to reverse distribute. So sine of x times what gives us sine of x, positive 1, and then sine of x times what gives us the sine x times cosine of x. Well, we need a negative cosine squared x, okay? That's step 1. And then you have to ask yourself, okay, maybe are there any substitutions we can make? And the answer is yes. This ends up being a manipulation, so we can move stuff around, of one of the Pythagorean triples, okay? It's called the Pythagorean, Pythagorean identity, just kidding. And there, I was thinking triple because there's 3 of them. Pythagorean identity. Pythagorean triple, that's a geometry thing, just kidding, right? But yes, so there's 3 identities. The first one, I know you've definitely seen this before, right? Sine squared, plus cosine squared equals 1. And then there's 2 other ones. The other 2 involves like secant squared and tangent squares and cosecant squares, right? So notice we can actually stop. How do we know it's going to be this one? Because if we look here, there's a cosine squared in it. So this is the only one out of the three Pythagorean identities that has a cosine squared in it. So obviously this is the one we want to look at. And also it has a 1 in it, right? So it has both a 1 and a cosine squared, which is where we see we're going to make some substitution there, right? So that's the one that we want to do. I'm not going to focus on the other identities right now. Okay, so we're trying to figure out what does 1 minus cosine squared equal to, right? Because we want to manipulate this so that we can make a substitution. So it turns out, right, we want to have 1 minus cosine squared. We can accomplish that by subtracting both sides by cosine squared, right? Because cosine squared x minus cosine squared x cancels out. And so we end up with sine squared of x. On the other side, those are not like terms, so I'm just going to write that as 1 minus cosine squared x. So that's it. We found out what 1 minus cosine squared x is, exactly sine squared x. So that's the substitution that I'm going to be making. I'm going to substitute that right into there. So I'm going to erase this and make that substitution. Okay, so now we're here. We've made that substitution. And then can we simplify it at all? That says sine of x times sine squared x. Yeah, I can definitely simplify that. And it turns out, right, totally on a separate note, if I asked you to do what's x squared times x, right? Or yeah, x times x squared is what I meant. That is pretty much like the algebra 1 version of that. Wouldn't that be equal to x to the third, right? Because you'd add the exponents. And so very similarly, that is exactly what happens here. This is actually equal to sine cubed of x. And look at that, we have actually reached our goal, so we are done. This is a 3-step verification. So next one, we're going to prove that this side is equal to the other side. So remember, you just pick a side and you copy it down. Typically, the more annoying looking one is going to be the easiest to do. And then just please don't forget, don't move anything on either side of the equations. This you are not touching at all. That's your goal, so you know you are done, okay? The other thing is I want to mention, because some people are actually, I've seen a lot of people do this, that they might cancel out the secant squares. Please don't do that. That's not correct. It would have only been correct if there was a times 1 on the bottom, okay? That would work then, but the problem is that it's subtraction. So you can't make that move. So again, you ask yourself, okay, well, are there any substitutions or algebra 1 simplifying skills that we could use? So it turns out that this is actually another Pythagorean identity. And remember that there are 3 of them. One of them we did see in part A, that's where the sine squared and cosine squared. There is one that actually does have a secant squared in it, and that Pythagorean identity is 1 plus tangent squared x is equal to secant squared x, okay? The third one doesn't have a secant squared x. That one involves cotan and cosecant. Okay, so obviously we're going to use this one, as I said, because this is the only identity with both the 1 and the secant squared, which is what we're trying to make that substitution. So again, we're trying to figure out, what does secant squared minus 1 equal to? Well, if we actually subtract both 1 on both sides, we'll find when we simplify, we're actually, it's not really simplifying. Yeah, I guess it's simplifying and also rewriting. Those are not like terms, so that's just secant squared minus 1. So we just found out that secant squared minus 1 is equal to exactly tangent squared of x. So that's the substitution that I'm going to make. So now that we made that substitution, is there anything else we can do? Well, there's actually a couple more substitutions. Secant is the reciprocal of the cosine ratio, right? And because the secant is squared, I can absolutely, totally legal of me to write it as 1 over cosine squared. If it was secant cubed, then I can write it as 1 over cosine cubed, so on and so forth, right? So this is over tangent squared. The tangent squared, I can write as sine squared over cosine squared, right? Because that is what the tangent ratio is. It's 1 over cosine. I'm sorry, it's sine over cosine. So because it's squared, it's I can square both of those. So now what we can do is use our algebra 1 skills. How do we divide fractions? We're going to keep, change, flip, right? So I'm going to keep the top, change it to multiplication, and then I'm going to flip the bottom. Okay, so that was just algebra 1 skills. And then how do we multiply fractions? You can multiply certainly straight across, or the shortcut is you realize diagonally you can simplify those cross out. And careful, sine squared is on the bottom, right? So that's equal to 1 over sine squared x. And you never want to lose sight of your goal, right? So if you're ever stuck, look up and say, where am I looking to go? I'm looking to finish at cosecant squared. But wait a minute, isn't that the reciprocal of sine squared? Yes, so actually, after we just equal this to cosecant squared x, we are done. So next, let's solve this quadratic equation using the quadratic formula. So before you even do anything, you have to make sure that it's equal to 0. So some people might say that the c value is -1. That's not correct at all. So in order to make it equal to 0, we would have to add 1 on both sides, right? So now that it's set equal to 0, and I'll write that down here in standard form, we're going to see that the c value is not -1, but it's going to be +1. Okay, so that's always your step 1. I like to tell people to, I guess, just write down what A, B, and C is, just to find those. So that way it's easy just to see when we plug into the quadratic formula. Okay, so now that's our A, B, and C values. So now it's just going to be a simple substitution. So as we make that substitution, that's the opposite sign of B. So it's -8, that's turned positive. Super important when you substitute, you have to substitute with parentheses here, or else the calculator is going to give you -64 as opposed to +64. And I can show that in the calculator in a second why that is. And we're going to do it all over 2 times A, which is 4. So I just want to show you really quickly that if you put -8 in parentheses, it'll give you +64. Now watch what happens if I put it outside the parentheses, it's going to give you -64. And the reason why it's doing that is because in this case, it's reading +8 as the base as opposed to -8. So it's doing +8 squared, which is 64, and then it's taking the negative of that. So just make sure also, another common mistake is when people are putting in the discriminant value, in other words, what's inside the square root, they'll accidentally do the negative sign, and your calculator is actually going to be multiplying. So the multiplication is actually a completely different button that you have to do. So just be super careful on that. So now the discriminant, or the number of the radical, is 48, right? So if the question was asking you to do it in, round it to the nearest 10th rather, then you would absolutely do the square root of 48. So then you would round to 6.9 and then go on as planned. But because we want to do it in simplest radical form, we don't actually want to put the square root in the calculator. All right, so this problem wants us in simplest radical form. So we did see that the discriminant, or the number inside the radical, is 48 all over 2 times 4, which is 8. And then a lot of people, what they would do is recognize, oh, 48 and 8, those are all divisible by a same common factor. They'll just divide it out. No, you cannot do that, because this is a radical and the other ones are whole numbers. And then people might argue, okay, well, maybe I can just cancel those out, or divide those by 8. No, you can't do that as well. And the reason why you can't is the rule of thumb is that all 3 whole numbers have to have something in common for you to do that. But if you say, wait a minute, I only see 2 whole numbers, there's an imaginary whole number here, 1, right? So if all those 3 numbers had something in common, then you could divide those. But given that 1 and 8, those don't have a common factor, you can't actually simplify that. So if you ask yourself, okay, but can I simplify it? Yes, you can. So you want to always check for simplifying radicals. So square root of 48, I'll do that on the side here. You can actually simplify that. And the biggest perfect square that goes into 48 is 16, right? You could use 4 and 12, but then you'd have more steps to do. The reason why I know 16 is the biggest perfect square is because then square root of 3, there's no perfect square that goes in there. So then the square root of 16 is 4, and then drop down that radical 3. So square root of 48 is the same thing as 4 radical 3. So if I now make that substitution, you'll see that now actually all 3 whole numbers do have something in common. So those I can divide all by 4. So 8 divided by 4 is 2. 4 divided by 4 is 1. You don't need that 1 there, but you can if you want to put it there. And then 8 divided by 4 is 2. So this is going to be your final answer in simplest radical form. So now we're going to get the same solution as the previous one. Notice it says confirm, so we technically already know what the answer is, but we're going to do it using a different method, completing the square. Okay, so completing the square is definitely something that you have to memorize. It's a process. So I'll write the original problem here. So I'm actually going to write it in standard form for 1 second. So remember before we had +1 equals 0? Okay, so because I want to talk about a few things. So from standard form, we want to make sure, right? And let me actually hold on back up for a second. When I'm referring to A's and B's and C's, I'm talking about A is the coefficient of x squared, B is the coefficient of x, and C is the constant. It doesn't have a variable attached to it. Okay, so we want to make sure first that A is +1. If it's not +1, then you have to make it +1. So how would we make it +1 in this case? We would have to divide by 4. But just make sure that you have to divide everything by 4, okay? Because then you're changing the problem. So now we end up getting x squared minus 2x plus 1/4 equals 0 divided by 4 is 0. So notice that technically you could use 0.25, but we're going to keep it as a fraction because again, let me go back to part A. Notice there's no decimals, so we're going to keep things as radicals, okay? So we're going to leave that as 1/4. So now that we have A equals 1, step 2 would be to move C to the other side of the equation. Okay, so in this case, adding 1/4, so we're going to subtract 1/4 on both sides. And so after this step, when you do move C to the other side, I would recommend, now in this case, we're going to add, leave a space on both sides, or I like to add boxes. And then 0 minus -4, so we have -1/4, right? So we're going to prepare to add the same number on both sides. So remember, as long as you add the same number to both sides of the equal sign, again, you're not changing the value of anything. I can I can add 7 to both sides. I could add 1,000,000 to both sides, right? So, but we're going to add a very special number to both sides, and then there's going to be magic that happens, okay? So for step number 3 is figuring out what goes in that box. So this is always the step. You're going to take half of B. In this case, B is -2. So half of B is -1. And then you're going to square it. Okay, so be careful. We're squaring -1. So -1 should be in parentheses. So that's a negative times a negative. So you should always, always, always be adding a positive number on both sides. Okay, because squaring gives you positive. Always. So if you get a negative, it's going to mess things up. So now why is adding 1 to both sides? Why will that help us? Because now this is called a perfect square trinomial, right? It's a trinomial, so there's 3 terms, but it's a perfect square because we're going to factor that. Now you can actually factor that using the AC method. Okay, and if you factor using the AC method, by the way, you're going to end up getting x minus 1 times x minus 1, right? If you FOIL that, you'll get back the original if you don't believe me. But isn't something isn't something times itself the same thing as that squared? Okay, so you don't have to use the AC method. The shortcut is, first of all, after you add that number to both sides, the template is then going to be x plus something squared. Okay, so now step 4 would be what goes in that box, right? So step 3 was figuring out what goes in those first set of boxes. Step 4 is now figuring out what goes in that box. And that plus could turn to a minus, right? Depending on the problem. So in this case, we are going to turn that into a minus. But what is the actual step? What goes in that box? Luckily, it's easy to remember. It's just going to be that the first step of step 3, okay? So that would be whatever half of B is. So take half of B. Take of half of, that's not it. Take half of B. Okay, so we already talked about half of B is -1. So I could just write -1, or you can write plus -1, doesn't matter, right? So that's what goes in there. And then we're going to simplify that right-hand side. So -1/4 plus 1, we need common denominators. That's the same thing as -1/4 plus 4/4, right? So that's going to be 3/4. Okay, so now we're here. So what was the entire point of converting it from standard form to something that looks like this? Is now finally we are in a scenario where we can finally solve for x, what's called using the square root method. And why would it be called the square root method? Duh, because the opposite of squaring is square rooting. And why would we want to do that? So now, as I said, because they're opposites, they're going to be, these are going to cancel out. And we do end up getting x minus 1 equals, now be super careful, a lot of people do mess up on the fact that whenever you take the square root of something, you better put the plus or minus, okay? So it should be plus or minus the square root of 3/4, okay? So when you take the square root, so I'll write plus or minus here. Just don't forget that plus or minus when you take the square root. So now, by the way, let's simplify this. What's the square root of 3/4? So whenever you have a fraction inside a radical, you can split up the radical top and bottom, okay? So that means the same thing. And then notice the bottom, that's a perfect square. The square root of 4 is 2, so I'm going to erase that and put 2. Okay, so now we're one step away of getting x by itself, so we're going to accomplish that by adding 1 to both sides. So we ended up with plus or minus radical 3/2, and then we added 1 afterwards. So how does this compare to part A? How can that possibly be the same answer? Is actually, if you add those guys, right, you need a common denominator. So that's like 1/1. So we're going to have to multiply these by 2, right? So that's the same thing as plus 2/2. Now that we have common denominators, you can actually combine the numerators. So that's going to be plus or minus radical 3 and then plus 2. Now, because of the commutative property, I can actually put that 2 in front and switch those and say 2, the positive 2, right? Because it says plus 2. So positive 2, and then notice the plus or minus is in front of the radicals. So I'm going to write plus or minus radical 3 all over 2. Does that look familiar? Yes, it does, because that is what we got when we did the quadratic formula. Now let's get into solving log and exponential equations. So first of all, first things first, what does ln even mean? Ln is a special type of logarithm. It's called the natural log, and it's called the natural log because it particularly has base e. So remember, e is actually an irrational number. It's just as famous as pi, but pi takes all the credit. Okay, so we see a lot in the natural world. We use that to model equations, and that's why it's called the natural log. So first things first, why don't we convert, or rather substitute, instead of ln, we can write that as log base e, because that's actually what it means. Okay, so we're going to do a few things, right? We want to get that x cubed, 27x cubed out of the log, okay? You can't just be dividing by 27x cubed, that won't work. So first, we can use the power rule. So whenever you have a number that's multiplied by the log, it says that you can actually convert that number that's being multiplied into that exponent. So that's exactly what happens, okay? So this is equal to log base e of 27x cubed raised to the 1/3 power, okay? So if you remember, when you have a fraction and an exponent, that converts to root. So raising something to the 1/3 power is the same thing as taking the cube root of that base. The entire base was 27x to the 3rd. Okay, so now we're going to simplify. It turns out, surprise, surprise, that 27x cubed is a perfect cube. So what times itself 3 times gives us 27x cubed? In other words, what is the cube root of 27x cubed? And that is going to be 3, because 3 times 3 times 3 is 27, and then x, because x times x times x is x cubed. So now we're here. Okay, so now that we have a simplified logarithmic equation, how do we finally get that 3x out of there? Is you're going to convert it to exponential. Think of exponentials and logs as opposite operations, if you will. So I like to kind of look at it as a little circle. So that is, if we convert it to exponential form, e to the second power is equal to 3x, right? Remember that when we convert logarithmic and exponential, the base of the log is e. That should always match the base of the exponent, right? So notice that both of those bases are e. So now, you know, it's not asking us to round to the nearest tenth or whatever, so you don't want to put e squared on your calculator. So now, again, what's the opposite of multiplying by 3? Dividing by 3. So x is exactly, so not rounding, e, I think it's like 1.7, yada, 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 right? It's an irrational number, but we're going to leave that as e squared divided by 3. That's the exact value of x. So now we have this fancier log equation. So whenever you have an addition or subtraction of two separate logs, very importantly, they must have the same base. Then you know you have like a product or quotient rule going on. So when you have a subtraction of two logs with the same base, that converts to, we're going to divide, these are called the arguments, okay? If there was an addition side, that would translate to multiplying them, okay? But this is the quotient rule. So again, when you have the same base, I keep stressing that because that's super important. We want to end up using the quotient rule. But before actually we do the quotient rule, I forgot this 2 over here. Remember, like in part D, whenever you have a number multiplied times a log, that's exactly the same thing as converting it or moving it as the exponent of this would be called the argument. So that would actually be step 1 before doing anything. Okay, so that's log base 3 of x plus 5 minus, now that becomes log base 3 of 2 squared. Okay, and what is 2 squared? I'm just going to erase that and put 4. So now that the coefficients of both logs are positive 1, that's when then you can use the product or quotient rule. In this case, it's quotient because there's subtraction. So this is going to condense, instead of 2 separate logs, we're going to put it in condensed form. In other words, we're going to convert it to 1 logarithm. So we had 2, now we condensed it to 1. And again, when you have subtraction of 2 logs, that's going to translate to division. So it's going to be left, it's going to be left over right? So x plus 5 over 4, and then drop down, that equals 1. So now that we condensed it to 1 single logarithm, you always want to do the convert it to exponential form, okay? So again, I do like my little circle thing. So that's 3 to the first power is equal to x plus 5 over 4, just checking that the base of the log matches the base of the exponent. Yep. Okay, so now what's left to do is to just simplify. 3 to the first is 3, so I'm just going to erase that to the first. And then this becomes really simple that we can multiply both sides by 4. So that's going to be 12 is equal to x plus 5. And then we can finally subtract 5 on both sides and get our final answer as x equals 7. So this is a really simple exponential function, right? You cannot divide by 2, which I see people doing from time to time. Nope, you can only divide by 2 if this was saying 2 times x equals 6. But that says 2 to the x power. This is an exponential. So remember, we've been talking about exponents and logs are kind of like opposites. So we want to convert this to a log expression. So remember, the base of the exponent better match the base of the log. Okay, so if people get confused what goes in the parentheses and what goes out, I like to just think of it again as that circle thing, right? So like 2 to the what power equals what? This would have to be x because it's 2 to the x, and then equals 6. You can remember it any way you want. I just remember it as a circle. So we want to solve for x. It doesn't say like to convert it to a decimal, so you can absolutely put that on your calculator, log base 2 of 6. Otherwise, we're actually done. That is what x equals. But what happens if you have more going on, okay? So whenever you have this type of problem, it's more often than not a situation where coincidentally, and I say that sarcastically because it's not coincidentally, you're going to have to convert those. Those are going to be the same base of the exponent. I don't know if that was confusing the way I said it, probably. So 81 is the same thing as what to what power? Well, that's the same thing as 3 to the 4th power, right? And what's 27, right? You just got to like play around with it. 27, I can actually write that as a base 3 to the 3rd power. So coincidentally, they happen to have the same base, okay? So in the spot of 81, I'm going to write 3 to the 4th, and in the spot of 27, I'm going to write 3 to the 3rd. Okay, so just make sure you put parentheses, right? So again, 81 is the same thing as 3 to the 4th, and then 9x plus 5. So I'm just making that substitution, and 3 to the 3rd would be 27. So the parentheses are super important because we're going to end up distributing the 4. And the reason is because this is the power rule of exponents. And when you have a power raised to a power, you multiply the exponents, okay? So we're going to distribute that 3 there as well. So we end up with, let's see, 3 to the 36x plus 20 is equal to 3 to the 21 minus 6x, right? So that's after we distribute it. So if this is 3 to the 36x plus 20, and that's equal to 3 to the 21 minus 6x, given those have the same base, then that means that these have to be equal to each other. So that would be the next step, right? So these would have to be equal to the same number. So that just becomes a regular multi-step linear equation, right? So it doesn't really matter what I do first. I can add both sides by 6x maybe. And so then we get 42x plus 20. And then we can subtract both sides by 20. And then we get 42x equals 1. And then finally, we can divide both sides by 42. So x is exactly 1 over 42, or if you want to round to the nearest tenth, whatever, you can do that. All right, solving trigonometric equations. So factoring, you're going to definitely have to know. So I like to tell people if they can get confused, this is totally optional, is to convert it from a trig equation to an exponential equation. So essentially, you're just taking out the signs. Okay, so that's going to be equivalent to 2x squared minus 3x plus 1 equals 0, okay? So you're just going to take out the signs, but then don't forget to put it back, right? So now this is something that our brains can comprehend, right? That is going to be a trinomial. The highest exponent is 2, so it's quadratic. So any quadratic trinomial, you always think of AC method, right? And by the way, very first step is actually, is there a GCF? Nope, right? So now we're going to use the AC method. So I'm not going to go super slow on this because I have talked about the AC method a lot in this video. So A is 2, B is -3, and C is 1. It's called AC method because we're multiplying A times C, so that's going to be 2. So a positive times a positive and a negative times a negative. We want the factors that add up to B, so it's going to be those factors. Now, this is not an A equals 1 problem. If it was A equals 1, then you could just pop those right into the template and you'd be done. But the problem is because A is not 1, you're going to take those factors and you're going to make them as coefficients. You're going to split up the middle term. So you're going to split this up as minus 2x minus 1x, right? Because those like terms add up to -3x. So I'm going to erase this and just rewrite everything. Right, so as I said, I'm going to split that up as minus 2x minus x or 1x, whatever. Right, so we have split up this middle term. Okay, why would we want to convert a trinomial to a 4-term polynomial? because now we're going to factor by grouping. And by the way, could I have switched these up? Could I have put minus x and then minus 2x? Absolutely. You'll get the same answer one way or another, right? Okay, so the GCF of this group, those both have a 2x, right? So pulling out a GCF, so I'm kind of blowing through this again because I've gone over this a lot of times in this video. So we're going to have two boxes here because there's two terms. So 2x times x gives me 2x squared, and 2x times a negative 1 gives me negative 2x. Done with that side. Now we're going to factor using the GCF of this group. Notice that there is no GCF. So whenever, this is only in factor by grouping, whenever that happens, you pull out a 1. Should I pull out a positive 1 or a negative 1? You have to play around with it. So it turns out that if you do take out a negative 1, what our goal is we're trying to get matching parentheses, right? So if I pull out a negative 1, let's see what happens, right? So same thing, two boxes because there's two terms. A negative 1 times a positive x is negative x. And then a negative times, this has to be a negative, gives me a positive, right? So if you pulled out a positive 1, these parentheses wouldn't have matched. So that's how you know, okay, maybe I should pull out a minus 1. So now that you have matching parentheses, the last step is to pull out or write that matching parentheses. And then what is left? The 2x minus 1. Okay, so now, again, we are solving for x. So don't forget this is equal to 0. And also we are not solving the polynomial equation. We're solving the trig equation. So now once you get it into factored form, don't forget to put the signs back. So where you see x, you're going to put sine of x back, right? So this should look like sine of x minus 1, right? So we're converting it back. And then that would be 2 times sine of x minus 1. All right, so how do you solve any factored form equation that's set equal to 0? Always, you're going to solve two separate equations. You're going to set separately this equal to 0 and this equal to 0, right? Two completely separate equations. So sine of x minus 1 equals 0, and then 2 times sine of x minus 1 equals 0. So we're going to solve as usual, like we would for a linear equation, right? You would add 1 on both sides. So on this side, we have sine of x is equal to 1. We'll solve that in a second. And on this side, we're going to add 1 and then divide by 2. Whoops. So that should be 1. And then we're going to divide both sides by 2. So on this side, we're going to be solving for sine of x is equal to 1/2. So we're going to need the unit circle on this. Now, whether you memorize the unit circle or you use reference angle is up to you. I'm going to just look at the unit circle since I like to memorize it. So we're going to first look at solving this equation, okay? What is this asking for? So remember that sine is the y value of the unit circle and cosine is the x value of the ordered pair in the unit circle, right? Remember, tangent is y divided by x and so on. You have to memorize all of that. So since sine is the y value of the ordered pair, what this is asking for is where does the y value equal positive 1 on the unit circle? Could be one spot, could be multiple spots. This over here, again, this is also a sine equation. This is asking where on the unit circle do you see a y value as positive 1/2 on the unit circle, right? Also could be one or multiple spots. So remember the first equation is we're solving for this one. So where do we see the y value as positive 1? Only in one location, right? And that answer is at pi over 2. So this answer, as I said, is pi over 2. Now, if we did a check, right? What that's saying is if I substitute pi over 2 in here, does sine of pi over 2 equal 1? Yes, right? So we know we did it correctly. Now, the directions, by the way, wants all of the angles. So in other words, pi over 2 would be going in a counterclockwise location, right? Is there a coterminal angle? Could I first spin around 360 degrees or 2 pi radians and then add pi over 2 to that? Yeah. Could I have a negative angle? Could I travel 270 degrees in that direction. Yeah, so notice every time I always land up in that y equals 1 location. So how do I write pi over 2 and all the coterminal angles in math language? And we would do that the following way. So we are going to write x is equal to pi over 2, right? So again, we're going to write well, we're not writing this, but I'm just doing this for you, and all the coterminal angles. Okay, so how do we write this? There we go. How do we write this in math language? We're going to write, and again, this is not in math language yet, but we're getting there. Another way of saying is all multiples of 2 pi, right? And all multiples of 2 pi. Why 2 pi? Because 2 pi radians, that's 360 degrees. Remember that we can add or subtract 2 pi radians to get to 360 degrees. So finally, how would we write and all multiples of 2 pi in math language? Finally, we're going to write plus, right? And bear with me, it's 2 pi, right? Times n, you could put the times there if you want. But we have to define what n is. N stands for a number, but what does that number? Could that be an irrational number? Could that be a fraction, right? So it turns out, how do we write multiples of 2 pi? N has to be an integer. Remember, an integer are like the positive and negative whole numbers. So we're going to write a comma, right? And we're going to write that n is an integer. Now, for my students, if people get freaked out by this, although in calculus you are expected to do this for sure, but if you're in a pre-calc, I would be totally fine if you were to write where n is an integer, okay? But in math language, okay, because math is a language, the other way that you would do that, which would be the way that you would absolutely do that in calculus, is write n is an element of, that's like the euro symbol. In other words, is the set of integers. Again, math is a language. The set of integers is like a z with a slash, okay? I know it's kind of crazy, but this literally means is an element of the set, or in other words, you could just look at that as is. And this literally in math language means the set of integers. Okay, so the correct answer would be all of this. This is saying pi over 2 and all the coterminal angles, or all multiples of 2 pi. Okay, so if we were to do a check, and I'm not going to do all of them, if you're still not convinced, again, n is an integer. So how about so let's start with n equals 0, right? So that is pi over 2 plus 2 pi times 0. Well, what's anything times 0? 0. So when n equals 0, the answer is pi over 2. We know that is an answer, obviously. How about when n equals 1? Okay, so that's pi over 2 plus 2 pi times 1. What's anything times 1? Itself. So that's going to be plus 2 pi. That's a coterminal angle because you're adding 2 pi. What about, so if you were to do -1, -2, right? If you add all the integers, you end up getting all the coterminal angles because you're going to be adding and subtracting 2 pi. Okay, so believe it or not, though, we are not done. This solution set was only for that left equation. Remember that we still have the other side of the equation to do. So let me erase this, right? So remember, the other side of the equation was sine of x is equal to 1/2, okay? So that is, where do all the y values equal positive 1/2? That's right there at pi over 6. And also right here at 5 pi over 6. So if, let's say, the directions was saying, I only want the solutions between 0 and 2 pi, there's only two answers, pi over 6 and 5 pi over 6. But the directions is saying I want also, or it doesn't say anything actually, but that's implying I want all the solutions. So again, you're going to have to do that fancy math notation, right? So instead of just pi over 6 and just 5 pi over 6, we are going to now add all of the coterminal angles. And how we do that is the plus 2 pi n, comma, where n is an integer, Same thing over here, plus 2 pi n, where n is an integer. So please add these two to the solution set that we got. The other one was pi over 2 plus all the coterminants. So for part H, this is not asking for all of the solutions. We want only those that are between 0 and 2 pi. Okay, so this is very specific. So there's not going to be infinite answers here, not with including all the coterminal angles. This is just finite amount of solutions. You can count them. Okay, so how would we do that? So again, if it scares you, that cosine, if you want to temporarily, right, just take the cosine away and just change this to a polynomial equation. So that's 1 over radical 3 times x, right? Minus 1 equals negative 1/2. If that's less scary for you, do it. Otherwise, you don't have to do the step, right? So just remember to put the cosine back after you're done. So you would have to add 1 on both sides, right? So now we have 1 over radical 3 times x is equal to, that's negative 1/2 plus 1. That's just going to be 1/2. Okay, notice I didn't convert it to a decimal because that's not going to actually help us here. We're looking to get a value that's on the unit circle. That's the whole goal. Okay, so we actually want to keep it as fractions. So now how do you get rid of that times 1 over radical 3 is you could do two things. One, the opposite of multiplying by 1 over radical 3 is dividing by 1 over radical 3. And then over here, you would have to keep change flip, right? The other way that you might have seen whenever you have multiplying by a fraction and you're trying to get rid of the fraction is it turns out you can just multiply by the reciprocal. Okay, and then when you multiply by the reciprocal, it actually does, this is the keep change flip, it does it for you. Okay, so if you did do the previous way, if you prefer the previous way and you keep change flipped, you would end up here, right? So how do we multiply fractions straight across, right? So 1 times radical 3 is radical 3, and then 2 times 1 is 2. So just don't forget, right? This is not the original problem. This was a cosine problem, so just don't forget to put that cosine back, okay? So that's the equation that we're trying to solve. Remember that sine is y and cosine is x. So this is asking us, where on the unit circle do you see the x value as positive square root of 3 over 2? And it turns out that happens in two locations. Positive square root of 3 over 2 as an x value is there. So one of the solutions is 11 pi over 6. And the other place where it's a positive x value is at positive pi over 6. So those are the two solutions, pi over 6 and 11 pi over 6. Done. Two things in this problem. So first of all, you have to recognize that we do not want all solutions. So you're not doing the plus 2 pi n where n is an integer like we did in the other problems. We do want a finite number of solutions. So there's not infinite solutions. You can actually count how many answers are there between 0 and 2 pi radians. The second thing that you probably have noticed is you have both a cosine function and a sine function in the same problem. So if you notice, like the previous problem, part H, that was only a cosine function. And if you look at the previous one, that was only a sine function. So what happens when you have a mix of both? What should go off in your head is this is probably some sort of another Pythagorean identity that we want to manipulate and substitute. And then it ends up turning into a situation where you only end up with a cosine function or only end up with a sine function. So first things first, what we want to do, right, is if you maybe connect to what we did in part G, notice that this was equal to 0. And when you feel stuck, that would definitely be something that you would want to focus on. So how can we make this equal to 0? Well, we can subtract 1 on both sides. So we get cosine squared x plus sine of x minus 1 equals 0. Now, remember when we actually did two problems ago, we converted it from a trig function to a polynomial function. But the reason that you can just take the sign away, right? So instead of 2 sine squared x, we did 2x squared. And instead of 3 sine x, we just did it as 3x. That only worked because you had one function, right? So in other words, if you were to try to convert this, right? If let's say you took out the cosine squared, which is equivalent to x squared in the polynomial, unfortunately, right, I can't just write plus, I can't just take the sign away and write plus x, right? And then minus 1 equals 0. This would be the wrong polynomial. And the reason being is because we are making a substitution where we see a cosine, we're putting an x. I can't substitute the x for sine because x is cosine. So technically speaking, if you wanted to convert this to a polynomial, the sine would have to be a separate variable. I don't know, I'm picking another one. It would have to be like y, right? So you can't ever solve an equation with 2 unknowns, right? So how would we make this into a scenario where we only have x's? Well, again, you would need a trig equation where you only have a cosine in it, or you only have a sine. And so whenever you see something squared, a bell should go off in your head. That's probably one of the trig identities, because if you remember the trig identities, those are all the squared functions. So what is the only one? There's 3 of them. What's the only one with the cosine squared function? And we did this in problem 11a, and I'll do it again. It doesn't matter because of the commutative property, but technically the first trig identity, the main trig identity is this, okay? Sine squared plus cosine squared equals 1. There are the other 2 which involve like tangent squares and secant squares and so on and so forth, but this is the one we want because it has the cosine squared. So we're trying to figure out what does cosine squared x actually equal, so that way I can make that substitution. And just like we did in part 11a, but I'll show it again, how do we get the cosine squared by itself? Well, if I subtract both sides by sine squared of x, in other words, I'm solving for cosine squared x, we'll find that cosine squared x is exactly 1 minus sine squared x. Great. So now that I know what cosine squared x is, it's equal to exactly 1 minus sine squared x. I can now substitute that in that spot. Okay, so what I'm going to do is erase everything, and I'm just going to put, as I said, 1 minus sine squared x in that spot. All right, so as you can see, instead of the cosine squared x, I put 1 minus sine squared x in that spot. So do we actually need those parentheses? I just showed you because I did the substitution. So you actually could just drop the parentheses. We don't need it, right? And now how can we put this in standard form? Remember, standard form is, well, actually, let me back up for a second. Can we simplify anything? And yes, it turns out that when you combine like terms, right? 1 minus 1, that cancels out. So now if I simplify, be careful, drop down that negative here. That's negative sine squared of x plus sine of x equals 0. This is actually in standard form already. Standard form is when you start with the highest exponent. So in this case, it's 2, and then it goes down in descending order. So that would be like to the first power. So actually, it is in standard form. And standard form is nice because you're looking like if you want to do the AC method, stuff like that. So it's just nice to put it in that order. It's easier for our brains to process that. So anyway, so we're looking to factor this. And actually, let me back up. Can we convert this to a polynomial now? And yes, because look what happened here. We started out with an equation with a mix of 2 trig functions, and now we have converted it without changing the value to a situation where now they're both the same function. Isn't that cool? So now you don't have to do the step and convert it to a polynomial. If you recognize that they both have sine of x, you can take out that GCF. Or for a lot of people, I find that it's helpful, they like to first convert it to a polynomial. So now you can just take these signs away, right? So instead of negative sine squared x, that's equivalent to negative x squared. And instead of plus sine of x, again, just take the sine away, that's equivalent to plus x, right? Those are going to be the same variable because those are both signs. So now if it makes it easier for your brain to process that, that is certainly easier to factor for a lot of people than looking at that, because that freaks them out. They see too many, they see too many letters. Okay, so now this is what we are looking to factor here. And then just don't forget, after you convert it to factored form, to make sure to put those signs back, right? So again, how many terms do you see? There are 2 terms. So you can't use the AC method, that's 3 terms, right? And besides, right, there are 2 terms. Is this difference of perfect squares? Obviously not. Sum and difference of cubes, right? That would be another scenario that you would look for 2 terms. Definitely not. So again, I have been saying this entire pretest anyway, the very, very first thing you always want to do when factoring is look out for the GCF. In that case, they both have a greatest common, there is a common factor between the x squared and the x. They both have at least 1x. Now, should we take out a positive x or a negative x? And in this situation, it actually doesn't matter which one you do. You'll get the same answer one way or another. So if I take out a positive x, right, I'll take the GCF out. How many terms? How many boxes? 2, because there are 2 terms. Reverse distribute. X times what would give me a negative x squared? I'm going to need a negative x. And then x times what gives me a positive x? I'm going to need a plus 1 equals 0, right? If, let's say, you took out a negative x, I just want to show it for those people. What would happen is that the signs inside the parentheses would change, right? Instead of negative x, it would be positive x. And instead of plus 1, it would have been minus 1. So it doesn't matter for each of them, you will get the same answer. So just don't forget, after you have converted it to factored form, don't forget to put it back. So put the signs back in the place of x. So instead of x, I'm going to have sine of x. And instead of negative x, I'm going to have negative sine of x plus 1 equals 0, right? So you'll find if you distribute, you'll get the same answer, right? Sine of x times negative sine of x is negative sine squared x, so on and so forth, right? Okay, so now what happens when you have any factor form equation that's set equal to 0? This goes for any equation. Anytime you have a factor form equation set equal to 0, you're going to have separate equations set equal to 0. So you're going to equal that guy to 0, and you're going to equal that guy to 0. So your 2 separate equations that you're solving is sine of x is equal to 0, and negative sine of x plus 1 is equal to 0. All right, so we're trying to figure out sine of what angle is equal to 0. So this is asking for 2 things. Sine, which translates to the y value of the unit circle. Remember, cosine is the x value of the unit circle. Tangent is y divided by x, so on and so forth, that you have to memorize. So we're trying to figure out where on the unit circle do you see the y value of 0? So you scan around the unit circle. I see y value 0 here and here. So the answer to this is between 0 and 2 pi, x would have to be 0 and pi. So those are your 2 solutions. So x equals 0, comma, and pi. Or you can write those separately, right? And if you wanted to do a check, right, sine of 0 equals 0, and sine of pi equals 0, right? So those are 2 solutions from that side. But then don't forget, we have the other side of the equation. Remember, that was negative sine of x plus 1 is equal to 0. So now we're going to solve for x there. Okay, so how do you do that? We're going to subtract 1 on both sides, and we get negative sine of x is equal to negative 1. Now, remember, this is like saying negative 1 times sine of x, so we're going to have to divide both sides by negative 1. So we have here sine of x is equal to negative 1 divided by negative 1. That's equal to positive 1. Okay, so what is that saying? Again, because we're looking at the sine function, we are now going to be scanning the y value again of the ordered pair, except where is it equal to positive 1? So looking around the unit circle, the only place with positive 1 as the y value is at pi over 2, right? At 3 pi over 2, that y value is negative 1. So there's only actually one answer here on this side, and that is going to be pi over 2, right? Because if we did a check, that would be sine of pi over 2 is equal to positive 1. Yes. Okay, so there are 3 solutions between 0 and 2 pi to solve this equation. That is 0, pi, and pi over 2. We're going to solve the systems of linear equations. It says using any method you see fit. So I'm going to go over using, if you wanted to use the linear combination method or the addition method as it's called, and the substitution method. So whichever method you could just, that you prefer, you could just, skip ahead. But I will, let's see, I can go over the substitution method first. So whenever you want to use the substitution method, you're always looking for which variable could I solve for? Could I solve for this one or this one or this one or this one? And what we want to do is we want to plug in one equation inside the other. I always tell people, look for which is the one that has a coefficient of 1. The only one that has a coefficient of 1 is going to be that y value there, right? And the reason being is that when we solve for something that has a coefficient of 1, there's a less likelihood that you're going to end up with fractions, because who wants to substitute with fractions? The other route, by the way, is if you were visual enough that all of these guys were divisible by 2, you can absolutely, if you wanted to, divide everything by -2, and then actually you have more options there. That ends up having a coefficient of 1, and so does that one, right? But let's say more often than not, people don't recognize that. I would say that the biggest probability I would assume is people would solve for that one. And you could do, you'll get the same answer one way or another. I would just say this is the easiest way. So I just rewrote that equation. So we want to solve for y. So we can accomplish that by subtracting 4x on both sides, right? And be careful, you want to drop down that negative. So it should be negative y is equal to, those are not like terms. So that's going to be 20 minus 4x. Now what we want to do is substitute this in for y in the second equation, but that's not equal to positive y, that's equal to negative y. So again, this is the same thing as -1 times y. So just don't forget, you're going to have to divide everybody by -1. So we now know that y is equal to -20 plus 4x now. So what we're going to do is going to plug in, now that we know what y equals, not the exact value, but good enough that we can now make that substitution. And so what we essentially have done is we are plugging in the top equation into the bottom equation. Other scenarios, it depends on the problem, you're going to plug in the bottom into the top. So I'm going to write that bottom equation here. And super important, when you make that substitution, you want to hug the y with the parentheses, right? Because every time you substitute, you should always substitute with parentheses. So if you don't, that's going to screw up your final answer, because now you should end up distributing that -2. Whoops. So when you make a substitution, right, now we're here. Now, by the way, let me back up. Super important that people don't make connections. What did this just do? This converted an equation that had 2 variables, which, by the way, is impossible to solve. You can't ever solve an equation with 2, 3, 4, 5, 6 different variables going on. Now we have converted it to a situation where now, look, there's only one variable, in this case is x. Only when you have one variable and you're solving one equation, that is when we can now solve it. So I just wanted to take the time to review that, right? Because that was the whole point of making that substitution. So now as we simplify and distribute, so that is going to be a positive 40 and a minus 8x. We can now combine like terms, so that's negative 10x plus 40 is equal to 10. We'll subtract 40 on both sides. So now we have, that would be negative 30, and then divide both sides by negative 10. So we get x equals 3. Now don't forget, this is actually not the final answer, as people would love to put a box around that. Doesn't matter whether I plug in x equals 3 in here or in here, absolutely not, because remember, it's a solution to both, okay? So it doesn't matter which one you do. Maybe I can do the top one, which looks a little bit less annoying. So as I rewrite that top equation, now I'm going to substitute that into the x spot. So now I have 4 times 3 minus y equals 20. Simplify. So 4 times 3 is 12. Bring down the minus y. Then we can subtract both sides by 12. Be super careful. Bring down that negative. A lot of people forget that. And then remember, this is like saying times -1. So we have to divide both sides by -1. And so now we end up with y is equal to -8. So remember that the final answer should actually be an ordered pair, because if we were to solve this by graphing, the answer would be that intersection point. So we would write the final answer that way. The other way we could do it is by, it's called the elimination method or linear combination or the addition method. They have three separate names. It's called the addition method because when we add the two equations together, something should cancel or eliminate. That's why it's called the elimination method. So right now when we add them together, right, and combine like terms, that would be 2x minus 3y. Notice nothing cancels out. And so when this happens, you're going to have to multiply one of the equations or both, depending on the problem. So what we're looking to do is we're looking to match the coefficients, and they have to be opposite signs. So two ways that you can accomplish this is if you were to multiply the bottom equations by 2, 2 times negative 2 is negative 4x. That's the opposite of positive 4x. Those would cancel. Or the other way is if you were to multiply the top equation by positive 2, that's going to cancel the x's. 2 times negative y, actually, no, I lied. You're going to have to multiply by negative 2 because a negative times a negative, that would be positive 2y, and that is going to be opposite of negative 2y. So those would cancel. So it doesn't matter which one you do first, you always get to the same destination one way or another. Maybe if we multiply the bottom by 2, so I would stay organized, right? We're not touching this, so I'm just going to rewrite it. And this is the one, don't forget, a lot of people distribute the 2 to those guys, but don't forget you have to distribute it to everything, okay? That's the catch. So then you get negative 4x minus 4y, just kidding, is equal to 20. And so now look what happens when we add them together. We already know those cancels. Negative plus a negative, so it's going to be another negative. 5y is equal to 20 plus 20 is 40. And then when we divide both sides by negative 5, surprise, surprise, y is equal to negative 8. And so now I'm not going to show this part, but if you substitute negative 8 into this one or into this one, it doesn't matter. You'll get the same answer because they're a solution to both. The only thing actually I will say, like if you substitute into the top one, a lot of people, I can guarantee you, not a lot, but yeah, no, a good amount of people, this is a common mistake. It's minus a negative 8. So this one actually should end up being 4x plus 8 equals 20. Okay, so be careful. So obviously, if you were to solve that equation, surprise, surprise, you would get x equals 3, which is what we got when we did the substitution method. I don't know what it is about rational functions, but like they're just so much fun for me. I don't know why. So when we asked to find the domain of the function, remember the domain is the set of all x values. So those are all defined. So in other words, if I'm just picking a random number, if I substitute 1 into the function, right, that's 1 plus 2 over 1 squared minus 4. So that's going to be 3 over negative 3. So that value is negative 1, right? That's defined. So we would say that 1 is inside the domain of the function. So at x equals 1, there would be a y value graphically if you were to graph it. So this is asking, is the domain all real numbers? Okay, can I plug in any x value and always get a defined answer? And the answer to this question, whenever you have a rational function, there's always going to be some sort of an exclusion, okay? Remember, a rational function is you have a polynomial up top and on the bottom. And so because you have a variable on the bottom, that's an issue. Because remember, when you have a fraction, the denominator can never equal 0. Because what happens if you have, like, let's say you have 4 divided by 0, that's not 0. This is undefined. People get confused about that. If you have a 0 up top, then 0 divided by 4 is 0. But remember, the denominator can't be 0. So whenever you're asked what's the domain of a rational function, how you figure that out is I don't care about the top. The top could be any number in the world. It's the bottom that causes the issue, right? So you're going to set the denominator to 0. I just like to put that slash as a reminder that it can't be 0, okay? And then you were to just solve any other way. Now, if you recognize you can actually factor this using the difference of perfect squares, or in this case, whenever you're missing a middle term, you can absolutely add 4 on both sides and solve using the square root method. right? So just don't forget though, because a lot of people do, whenever you're solving for x and you take the square root, it's always going to be plus or minus. So there's actually two different answers here, okay? So your two answers would be that x cannot be equal to 2 and x cannot be equal to -2. That is the domain of the function. Now, depending on your teacher, they might probably want you to write more fancy, right? It's the set of all x values such that x cannot be equal to 2 comma -2. That's like the fancier math way to do it, but usually, that should be fine. Just ask your teacher. So if you were to do a check, I'm not going to check both of them. What happens if we just plugged in +2 into the function? That would end up with 2 plus 2 divided by 2 squared minus 4. So that would give us, if we simplify, 4 divided by 0, undefined. So the domain of a rational function is highly connected to discontinuities and vertical asymptotes. And when you get to limits in calculus, you're going to find the limits. Okay, so super important. So whenever you find the domain of the function, what x cannot equal, these are called discontinuities. Okay, one discontinuity, two discontinuities. So it's where it makes the function discontinuous, right? A continuous function is if I were to just draw, any polynomial graph, for example, that's continuous because a way that I tell people is you never pick up the pencil when you graph the function. A discontinuous function, the second that you pick up your pencil to draw the graph, there's a discontinuity at that point. So maybe it could be a piecewise function. Maybe it could be a rational function is another one. So I'll talk more about the discontinuous at the end when we are going to graph it. You can see it visually. So anyway, anytime you find where the denominator equals zeros, those values are called discontinuities. Now, when you are asked to find, are there any vertical asymptotes, AKA, those are called infinite discontinuities. What you do is you're going to substitute the discontinuities into the function. And the rule of thumb is two things. If you substitute a discontinuity into a function and you get some number, it could be any number over 0, right? That is how you know that there is a vertical asymptote. I'm abbreviating here vertical asymptote. So that's what we're looking for. If, by the way, you substitute into the function and you happen to get both a 0 up top and the 0 on the bottom, that's actually called indiscriminate. And that actually is going to give us information that we know there's going to be a hole there. And that is actually what part C is asking. So this is what we are looking for. So for part B, we're looking to see which one of those, when I plug it into the function, gives us some number over 0. And actually, when I did that check before, remember when I substituted 2 into the function and we got 4 over 0? That is a number over 0. So actually, we know that there is a vertical asymptote at the x value 2. So now what happens when I substitute the other discontinuity into the function? So I get -2 plus 2, and then divided by -2 squared minus 4. So -2 plus 2 is 0. -2 squared is +4. 4 minus 4 is 0. There you go. So now you end up having a 0 divided by 0. That answer is called indeterminate. And what this means is it's not exactly known or defined, right? The answer is not 0 and the answer is not quite undefined, right? This is called undefined, by the way, when you have number over 0. Okay, and then this is called indeterminate. We don't really quite know what that means. So now, because we have 0 divided by 0, this is actually going to be the answer to part C. So there's going to be a hole at -2, and it would be because of this. That's the work. We know this function has a vertical asymptote and a hole. The question is, does it also have a horizontal asymptote? And the answer is yes. So there's two ways that you can have a horizontal asymptote. First things first, when you're asked this question, you want to find the degree of the polynomial up top and on the bottom, okay? So the polynomial at the top, x plus 2, has degree 1, right? It's to the first power. The bottom one has degree 2, okay? So that's step 1, is identifying the degree. And then, as I said, there's two different scenarios. Either it's what I like to call Bobo, and the other one, I like to remember it as eats delicious lava cake, DLC, delicious lava cake. So it's either Bobo or eats delicious lava cake. So here's what they stand for. This is if it's bigger on the bottom. This is actually like a 0. So if the degree is bigger on the bottom, there's going to be a horizontal asymptote, HA, I'm abbreviating, at the line y equals, and then that's like a 0. So in other words, the x-axis, okay? If the exponents are the same, and that's what these stand for, exponents are the same, then DLC stands for, you can find the location of the horizontal asymptote. You divide the leading coefficients. Okay, so D stands for divide, L stands for leading, and then C stands for coefficients, in which I abbreviated. Okay, so if you notice, it is bigger on the bottom, right? The bottom is degree 2, that's bigger than degree 1. So therefore, this has a horizontal asymptote, HA, at the line y equals 0. In other words, the x-axis. If, let's say, for argument's sake, let's say the exponents were the same. So let's say this top here was to the second power. Then what you would do is divide the leading coefficient. The leading coefficient is the coefficient of the term with the highest exponent. So those would both be 1. So you would find the location by, it would be 1 divided by 1, which is 1. So if that was the case, there would have been a horizontal asymptote at the line y equals 1, okay? But the original problem was this one, so it was the Bobo. So again, I go through all of this extensively in my course, link below. But anyway, this is all the information we found in this problem. So there's a vertical asymptote, VA, at x equals 2. There's a hole at the x value -2. And then we just found that the horizontal asymptote was at y equals 0. So I do just want to add that this is, so the vertical asymptote is a line. The hole is obviously a point. So that would be an open circle, right? At that point, that's what the hole means. And then the horizontal asymptote is also a line, right? Vertical, and I should say the vertical asymptote, it's obviously a vertical line, and obviously horizontal asymptote, it's a horizontal line. So that's why those are called the way they are. So let's sketch all of this information. All right, so if we have a coordinate grid, so there's going to be a vertical asymptote, which we do that drawing a dotted line. An asymptote just means that the function approaches it forever, but it never actually touches it, okay? And then there's also, so this is the line x equals 2. And then there is a horizontal asymptote at the line y equals 0, aka the x-axis. So this is the line y equals 0. So we know there's going to be a hole at -2, right? So if this is 1, 2, -1, -2. Okay, so usually these rational functions, let me just point out, right? So the parent function, y equals 1 over x, that's the parent function. That looks like this, okay? So it's always going to look like some sort of that form. So we are going to sketch this as there's going to be a hole here, and then it would maybe be something like this. Okay, and you can also use your calculator to help you figure out more of the picture. Speaking of parent functions, a parent function is practically like the most basic of all the functions. So this is a degree 2. So any degree 2 polynomial is actually a parabola. So all of these parent functions, you're going to notice, cross through the origin, okay? So a parabola, when the degree is 2, it's going to be a U shape. When it's the absolute value in part B, that difference is it's going to be a V shape, right? Those are two linear lines pointing with the vertex at the origin. So same thing, these are going to cross through the origin. The square root function is only a quadrant 1 function. It looks like that, okay? And then last but not least, a cubic function in part D, that kind of looks like that. Okay, so kind of like a little sideways S. So those all go through the origin. So now what does a sine function, a parent function, y equals sine of x, between 0 and 2 pi? So for sine and cosine functions, the parent function, it completes one full cycle, aka the period. So for both of these, I'm actually going to set them up the same. Okay, so the only difference between a sine and a cosine function, a sine function looks like a sideways S, and a cosine function looks like a U. The sine function, right, this is called the midline, it's the exact middle. And this is, by the way, I forgot, between 1 and -1. So a sine function, as I said, looks like a sideways S. So the beginning, middle, and end of those critical points are going to be at the midline. It's going to first go up to the maximum and then down to the minimum, right? So if I connect these points, you can see that it's going to be a sideways S. The difference between the sine and cosine function, by the way, is that here the first ordered pair of the is the origin, and then in cosine, the first ordered pair is actually going to be at 0, 1. So that's the difference, okay? So same midline. So the difference is the cosine function actually has 2 maximum values. In order to look like a U shape in the middle, it would have to be down at its lowest point. So the second and the fourth critical points, the main x values is going to be on the midline. So that's what a cosine function looks like. And remember, instead of starting at the origin, it's actually going to start at 0, 1. The tangent function, the period actually is pi radians instead of 2 pi, but the standard is going to be centered around the origin. And one period of a tangent function is going to be between -pi/2 and +pi/2. Now, these are the first and the last critical points. Those are the vertical asymptotes. The exact middle is 0, right? And then the exact middle of those would have to be -pi/4 and +pi/4. So a tangent function, it also kind of looks like a cubic function in a way. So that middle critical point, it's going to be over there. It's also going to be -1 and +1. So it's going to, as I said, kind of look like that cubic function. So it should look like that. So this is not asking to sketch it. It's just there's 4 transformations that you want to list. So there's actually 4 different things going on. This is a separate transformation. This is a separate transformation, the +1 and the -2. So whenever you have inside the function like this +1, that's a horizontal shift. So it's either left or right. People dislike the fact that actually this is going left, believe it or not. People would want to say right. But when you want to do horizontal shifts, it's actually the opposite than when you think. Vertical shifts is if you add or subtract outside the function. Notice it's outside the radical. That would be more of the intuitive. If you think minus, you would think it's going down 2 units. So that vertical shifts are exactly what you think. Anytime you have a negative, so if you have it on the inside versus the outside, notice this negative is on the outside of the square root. This is going to be a reflection, right? So anytime you see a negative, it's both reflections, but on the outside, it's going to be a reflection over the x-axis. If we saw, let's say this negative was on the inside, then it would have been a reflection over the y-axis. And last but not least, we have this multiplication of the 3 going on. So since that outside number is bigger than 1, then that means it's a vertical stretch. Okay, so it's like if I were to have a rubber band and I stretched it this way, the graph would actually look skinnier. If, let's say, that outside number was between 0 and 1, it would have still been a vertical transformation. It's either stretch or shrink. So if that was true, then this would have been a vertical shrink. So vertically, I would have smushed it like a pancake, right? So it would have gotten fatter. But again, since that outside number is bigger than 1, that's just how it goes, it would have been a vertical stretch. So in trig functions, there's amplitude, period, phase shift, vertical shift. So there's all those vocab words. So the amplitude, again, I talk more about this in the course, so I'm not really going to talk about it too much, but it's pretty much the distance from the midline to the maximum, which is the same thing as the distance from the midline to the minimum. And because that distance is positive, it's going to be the absolute value symbol. And particularly, it's going to be that A value. What am I talking about in terms of A, B, C, D, by the way? A is the coefficient, if you will, right? It's the number in front of the sine or cosine. That B value is going to be the coefficient of the x. That C value is going to be what's added and subtracted inside the parentheses versus adding or subtracting outside the parentheses. That's actually the D value, okay? So the absolute value of A, notice this A value here is negative. So remember, it's going to be positive 1/3, right? Because it's distance. That negative, by the way, that would have just been a reflection over the x-axis. That's what that would mean. Okay, so again, the amplitude is 1/3. The period formula is actually 2 pi divided by the positive of b, right? The absolute value of b. So in this particular case, b is 3, right? It's the coefficient of the x. So if we just pop it right into the formula, it's going to be 2 pi divided by the absolute value of 3 is 3, okay? So remember, the period just means how long it takes to complete one full cycle. So if it's cosine, how long does it take to make that U shape? So phase shift, that formula is the C value divided by the B value. So if we look up top, the C value is actually pi, right? And the B value was 3. So if we make that substitution, it's actually pi divided by 3. And the phase shift is another word for horizontal shift. So in other words, it went left or right. So again, in transformations, this actually would mean it went to the right pi over 3 units. Okay, remember, if it's inside the parentheses, it's opposite direction than when you think. Last but not least, vertical shift is that D value, okay? And the D value is positive 1. And so whenever you have an adding or subtracting outside of the function, or the parentheses rather, that, because it's plus, it is going up. Okay, so this would be going up 1 unit. We are towards the end, my friends. So this is super important in calculus because you're going to do limits like crazy. So this is to prepare you. So first things first, is this a continuous function? A continuous function, the best way I could just describe it to people is, can I trace the graph without ever picking up my pencil, right? So if it's coming from the positive infinity side, right, then I go up, then I go down, then I go up. Notice I traced in it. I didn't pick up my pencil once. So when that happens, yes, it is a continuous function, right? There's a flow continuously. So we're going to find the end behavior, and then we're going to find the domain and range. So the end behavior is called the end behaviors because as I go to the negative infinity towards the right, what's the graph behaving like, right? I don't care that it's going down and then it's going up and then it's going down. In the end, right, notice it's going up forever, right? So I don't care about what's going on in between, but as x approaches positive infinity towards the right, notice the arrow's going up and it's going to the positive infinity sign. And it turns out that both, right, as x approaches negative infinity. So as I travel, whoop, I did an 8. As I travel to the left, right, so if I'm going in this direction, right, I'm going down and then up and then down, right, in the end, it's also going up to positive infinity. So those both answers here would be positive infinity. You can put the plus sign here, but you actually do not need it. So the domain of this function is actually going to be all real numbers, right? So again, the domain is the x-axis. So all of the points, right? If I just graph this point, this point, this point, this point, right? They're all going to be points. So you can either write the domain in this notation between negative infinity and positive infinity, Or the other way is the definition of a domain is the set of all x values such that, and you can write all real numbers. Now, depending on your teachers in the past, remember math is a language, you might have seen like an R with a slash. That actually literally means all real numbers in math. So there's many ways that you can write it. The range of this function, remember the range is only the y values, okay? So if you look down here, there's nothing there. If you notice the y value 0 and up, right, all the y values greater than or equal to 0, that is going to be the range. So again, if you want to compare notation, you can either do 0, right? Make sure to put the bracket around the 0. That just means it exists at that point, right? There's a closed circle. A parentheses means an open circle, right? And then it goes to positive infinity. By the way, you can never, ever, ever have a bracket around the infinity symbol because that one means it would stop at a certain point, right? But there's no cap. It just keeps going on forever and ever. So now part B, is this a continuous function? So remember I said before, if you trace the graph, right? So I'm going to trace it down. Now, look what happens over here at x equals 1. I have no choice to pick up my pencil or pen, whatever, right? And then I have to jump. And then, right? So this is actually called a jump discontinuity. There is such a thing. So it's discontinuous. There would be, so this would means there is a discontinuity once you get at this x value 1. There's your problem. It's discontinuous at that value. So now if we talk about the end behavior, right? As x approaches, remember this is x. So as x approaches positive infinity, again, I don't care about what happens in the middle. I care about what happens in the end, right? In the end, right? So if you do trace, right, it's coming here, and then I have to pick up my pencil, and then I'm starting over here, and then it keeps continuing on and on and on. So because it's going down, right? It's going down to the negative infinity. Remember, this is the y-axis. It would be negative infinity. Whenever you have an arrow going up, it's positive infinity. When you have an arrow going down, it's negative infinity, right? So that answer is going to the negative infinity. As opposed to if I am approaching, right, this is x, if I am approaching the negative, right? So if now I'm coming up from this way, right, I pick up my pencil and then I trace it, notice at the end, it's going to always end up going up. So that answer, when x approaches negative infinity, we would say that the y values are approaching positive infinity. Okay, so we would write it like this. And again, for the second one, you don't have to put the plus sign, but a lot of teachers and textbooks do, but it doesn't matter. If you don't put it, it's understood as positive. All right, so now we're going to do the domain of the function. This is a little tricky, right? So remember the domain are all the x values. Okay, so if you notice that exists, that point exists, that point, right? These are all points, points, points. Now, again, at this x value 1, right? This is the x value 1. There is a hole here, and that means that it doesn't exist at 1. So people might think, oh, it's all real numbers except at x equals 1. However, at x equals 1, we also have this ordered pair. And because it's a closed circle, now it exists. Okay, so actually, it's going to be all real numbers. Okay, so all real numbers, I went over the both notations in part A, so I'm just going to write it like that. So again, now we're looking at the y values. So over here at the y value 4, right, there's that open circle. So people might say, oh, it's all real numbers except y equals 4. However, at that x equals 1 spot, this y value here, let's call it negative 0.5, right? It does exist there. So then some people might say, okay, it's all real numbers then. But then don't forget, if you notice, if I kind of zoom in, so if I zoom in really big, so if this is negative 0.5, right? And this is y value 0, notice right here in green, there's nothing there. So we would say that the range is all real numbers except those y values between negative 0.5 and 0. So how would we write that in math notation? So depending on who your teacher is, you can actually, maybe he or she might have you like physically write all real numbers except between negative 0.5 and 0, right? Or in math language, you might have seen this notation, right? It's coming from the negative infinity. Remember, it's the y values. up until the y value negative 0.5. Now we want to put a bracket around it because there is a closed circle there. It's implied. So at negative 0.5, there is a point there. And then we want to jump. So then the next part that the range occurs is at 0, right? So then we can say union from 0 to infinity. Again, and I talk about this in my course, okay? So that's one way you can say it. The other way you can say it, and some people might prefer this, maybe you can break it up as all the y values that's less than or equal to negative 5, and then you can put a comma, all the y values that are greater than or equal to 0. Last but not least, we're going to be doing a challenge problem, and I'm calling it a challenge because this is actually a calculus pre-assessment that I'm going over. So obviously, as you're going to take a calculus course, this is like the norm. This is what you're expected to do. So this is like a precursor or a prerequisite. So first things first, is this a continuous function? So remember that a continuous function, you can tell if the second I pick up as I'm tracing the function, if I am picking up my pencil, immediately it's not going to be continuous. So as I am coming from the left, right, I'm tracing. Now I have to pick up my pencil in order to now start to trace it in that direction. So obviously this is not going to be a continuous function. In other words, this is called a discontinuous function. Notice there is a horizontal asymptote here at the line y equals 0, aka the x-axis, right? And over here, there is a vertical asymptote, VA, and that is the line x equals 0. So there's a discontinuity at the x value 0, we would say. Now notice that I didn't talk about the y values. So discontinuities is more the x values. So as we're doing the end behavior, remember that the end behavior is, I don't care the stuff that's going on in the middle, but I care about what happens as x approaches to positive infinity. And remember, right, the x-axis is over here. So as I am going to the right towards the positive infinity sign, again, as I said, I don't care about where I'm going in the middle, right? So as I am coming from that direction, right, then I have to pick up my pen, and then I'm coming from that direction, right? So in the end, I'm actually approaching, now this answer is not going to be positive infinity. Positive infinity is if I'm going up. Negative infinity is I'm going down. So this is actually flatlining. So as x approaches positive infinity, right, it's going to be approaching the y value 0. And that is connected 100% because there is a horizontal asymptote there. So now as x approaches negative infinity, right, again, this is the x-axis. So as I'm approaches negative infinity, now I'm coming from the right. So I'm going to be tracing the function now in this way, right? Then I have to pick up my pencil, and now I'm starting from down here and I'm tracing it, right? So as I forever go to the left, again, your answer is not going to be positive infinity or negative infinity. Again, it's flatlining towards that horizontal asymptote. In other words, that y value 0. So both of these, as x approaches positive infinity, it's flatlining at 0, right? And it approaches also the y value 0 as x approaches negative infinity. So now, right, this is definitely what you're going to do in calculus. What happens if I'm approaching the x value, positive 2, but I'm coming from the left? So here is the x value, positive 2. Now what happens as I am approaching that x value coming from the left? So here is that left, right? So I am tracing the function this way. What happens as I am approaching that x value? It is going down to negative infinity. So that is going to be different for as I am going to be approaching the function coming from the right. So I'm looking over here. As I'm approaching that x value 2, that answer is going to be, it's going up to positive infinity. Okay, so again, as x approaches 2 coming from the left, it's negative infinity. And as x approaches 2 coming from the right, it's going to be positive infinity. So remember that the domain are all these x values here. So the question is it going to be all real numbers? And the answer is no, because again, if we look at all of these x values, the problem is at x equals 2, there's a vertical asymptote. And that pretty much means it's like an imaginary line that the function approaches. All the points get so close to it. And actually, it's forever and ever and ever. It's kind of hard for our brains to comprehend that, but it approaches it forever and ever, but it's never going to exactly hit the value x equals 2. You can write it in two ways. You can either write it simply as it's the set of all of x values such that x is not equal to 2. That would be the simplest way. The other notation you can write is as x approaches negative infinity up to 2, union, and then starting from 2 and then going on to positive infinity. Notice that I did not put brackets around the 2 because the x value 2 does not exist. So you're going to have to put parentheses, meaning that it gets really, really close to 2, but never actually touches. So now the range are the set of all the y values. So we are going to be looking at all of these values here, right? So again, you want to ask yourself, is it all real numbers? Is there any part of the graph where we see that it does not exist? And of course, here is that y value 0, right? So because there's that horizontal asymptote, it's very similar for the vertical asymptote at x equals 2. Now the range, it's going to exist everywhere except y equals 0. So for the same reason, so you can either, again, use this notation, all the set of y values such that y cannot be 0, or connected in the other way, that union, it can look like from negative infinity to 0, union, and then from 0 to infinity. So either notations is fine. Congrats, you made it. You made it through the whole pretest. I hope this was helpful. So just a reminder, I left a link in the description. I have a whole course on all the prerequisite skills in detail, modules, lessons, homeworks, quizzes, warm-ups, stuff like that. So just as you would for a regular class. So as I said, I'll leave a link in the description onto my website, and I hope I'll see you soon.